like how you would tune the observation errors in making reanalysis or making operational forecasts. Yeah, and then we plan on assimilating a bunch of observational constraints, but then we're not completely sure as to how we will introduce these constraints, particularly associated with like the thickness or the freeboard or even like snow depth observations. So if there are any inputs on what observations are out there and like what we should use, what we should avoid doing when making these sort of reanalysis, it would be great to receive advice or input from the members here. And finally, this is just another thing that we can do easily in this framework. We can even like try assimilating like synthetic observations called an observing system simulation experiment to try to test out like the benefits of different types of observations for improving your sea ice estimate. Yeah, so that is it for the talk today. Thank you.
I'm just to keep us on time. We have a remote presenter coming up. I'm going to ask you to direct questions to Heesung at break or at lunch or by email. Does that sound okay?
Yep.
Thank you so much. Our next speaker is Sky Gale.
On time mostly. Okay. Morning, everybody. I'm gonna switch now and talk about internal variability in observed model differences that we see in Arctic amplification. And first, thank you to all my co-authors because they've been very tremendous in this process. The motivation behind this comes from the fact that models rarely capture observed springtime Arctic amplification, or AA for short. So when you take a seasonal cycle of AA, which is this factor we calculate using the Arctic mean surface air temperature trend over a certain period of time, divide by that of the global mean. All this work is 1980 to 2022, so 43-year trends. But the seasonal cycle shows a huge difference in particularly the springtime, and you see it really pop out in April between the models and the observations. So this paper is just showing, I think, CMIP6 model mean with this horizontal brown line and then various model statistics with the box plot. Yes. Interestingly, the actual surface air temperature trend itself, so not normalized by the global mean, trend lies within the intermodal spread, suggesting it could potentially be due to internal variability. And there was a grad student who recently graduated from UW who reconciled this difference in the annual mean AA. So he was looking at this problem right here. He used machine learning, so I'm going to explain that method to you. And I'm tackling this problem over here. And to set up what this looks like spatially, I'm showing you the observed mean, what's called local amplification. So I've just taken, the surface air temperature trend at each grid point, again for 1980 to 2022, and divided by the global mean of the same time period. Observations on the left, and our multi-model mean is on the right here. When you take the Arctic mean surface air temperature and divide by a global mean, our observed mean AA factor is about 4.2. So observations are showing that the Arctic is warming 4 times faster than the global mean. For the multi-model mean, it's only about 2.7. And there's definitely a large difference between the patterns that you're seeing, which you would also expect comparing observations to multi-model mean, but it's very interesting just to look at where it's different. So our goals here, we're going to quantify the role of internal variability in the spring mean, and then we've also done monthly work for March, April, May, which is our spring months, with the machine learning method I will explain. And then we can compare simulated spring A, so that from the multi-model mean, to observations after we remove our internal variability estimate. For the observations and training data I use for this, there's a lot. I wanted this to be very thorough. Observations are usually an average of these 4 surface air temperature data sets. And then for sea level pressure, I use 3. Models, I have 12 large ensembles, which is defined as anything with 10 or more ensemble members. So I have them all listed here and the number of ensemble members I've used from each. And then I splice together a long extended period of each model or large ensemble to use from its historical and then either of those scenarios given what was available. And from this period sampling space, I can take 43-year trends, regularly spaced at 5-year intervals, to create a lot of simulated data for myself. So from models, I'm using SAT and SLP trend maps, and then simulated internally and externally generated trends. So the externally generated trends will be the ensemble means, and internally generated trends are going to be the ensemble members' individual deviations from that ensemble mean. So I use a convolutional neural network, or CNN for short. CNNs are very good at image classification, and this is a very niche utilization of this purpose. So my training data, as I said, is going to be SAT and SLP trend maps. These are my predictors, and these are all simulated data. And what I want the CNN to do is convolve these two variables with each other to best learn large-scale spatial features that it can establish a relationship to the internal and external SAT trends with. So I want it to figure out what that relationship is in all my simulated data. And I have an Arctic CNN and a global CNN that I'm using. So they're each trained separately and then outputted separately. And to give you an idea of the amount of data I'm putting in, so I have my two variables on the respective lat long grid for whichever CNN I'm doing. I have the X number of 43-year periods I can calculate from that period sampling space. And then I do a leave one out cross validation for every single large ensemble. So at any given time, I have 11 large ensembles I train on and one that I'm testing on. Of all the ones that I'm training on, I use 10 randomly selected ensemble members, so I don't weight my CNN towards any one particular model physics. And then, as I said, I run this through my CNN, and then the test is to predict the internally and externally generated trends of every single ensemble member of my cross-validation model, so I can compare the data for, it's the 1980-2022 period for every single ensemble member. And the last step, after I train and validate the CNN, is to apply it to observed SAT and SLP trend maps. So when I say apply, I just give the CNN these maps, and it should, after all of my training, have learned this relationship I want it to, and output what it thinks the internal and external SAT trends are, both the Arctic and the globe for observations. And the novelty here is that the CNN doesn't know what's model and what's observation. And we are assuming that somewhere in our model spread, we're hopefully getting the observations in there, which the SAT trend, as I said, does lie within the model spread. So we have pretty good hopes that this is working. So this is the output, and there's a lot that you can do with this. I think there's a lot of problems you can investigate from this that I haven't even gotten into. But what I'm showing you here at the top is the output from the Arctic CNN, and the bottom is the global CNN. The left is the internal predicted on the x-axis and the actual trends that we've calculated before on the y-axis. Internal component, the middle column is the external, and the right column is the sum. We don't predict the sum. This is adding the first two columns, and it adds another really nice check to make sure our CNN is not predicting some like outrageous external value for a model. Essentially, the closer that the dots are to the one-to-one line, the better our CNN is performing. You see, it does a pretty good job for all of the models. And the important thing is the vertical lines in each of the first two columns. So this is the observed predicted trends that our CNN is outputting. And then it's really small on this screen, but we have a mean predicted observed internal Arctic trend that we can calculate. So for this work, it's 0.21 Kelvin per decade. We have the same thing for the globe. And what we can do now is calculate an observed forced spring AA by removing these internal components from the actual trends in the Arctic and the globe. And we get 2.7. And this was a little worrisome at first, but I feel pretty good about it now. The observed mean AA was 4.2 originally, and the multi-model mean was 2.7. So we removed internal variability in observations and reconciled that difference, showing that it is internal variability in the spring. But we started looking at this monthly because I first plotted SAT and SLP maps of just observations. And it got really interesting in the monthly case. So what you're seeing here in the fill contours is SAT trends, and then the line contours is SLP. And the largest circulation anomaly that we see is in March, but the largest temperature anomaly we see, trend, I should say, is in April. So there's this really interesting problem going on in observations. And as you can imagine, the multi-model mean doesn't show the same variation as observations. So I'm just showing again the SAT from observations at the top and the multi-model mean on the bottom. Interestingly, so there is this variability in the SAT trend from observations. There's slight cooling in North America, and there's been a lot of good work exploring that phenomenon. We're focused on this warming across continental Siberia, particularly in April. And the multi-model mean has this more uniform warming signal across the Arctic, which you would expect from the forced response, with concentrated warming in the Barents Sea, particularly in March. This will go. Okay, so then we were wondering what could possibly be going on. So we're taking here now the difference between observations and the multi-model mean at the top, and these wind nudge runs, which they're called PI nudge in the paper, is Jen here? No. So this is from Jen student Ash. They did a really wonderful job with this work, and it's also some of the best documented code and model output I've ever seen. It was really nice to work with. But this is an ensemble of CSM2 pre-industrial control nudged to Era 5 winds in the horizontal at 850 hectopascals and above from 60 to 90 north. And their goal here was to isolate the influence of observed winds on Arctic climate. So not necessarily internal variability, but they wanted to understand the role of the winds. And what we did was we took pattern correlations between our difference of observed and the multi-model mean to these PI nudge wind nudge runs. And it is very high, especially for April. It's about 0.82 for those of you that can't see it in the back. So we took this as all of this internally driven warming that we've been talking about and quantifying is clearly tied to wind driven warming. So when you get the winds right, you can get this warming pattern right. Conversely, we've been in kind of internal variability space, but because the difference seems to match the winds pretty well, you can also take this to mean that our forced SAT trend pattern is actually supported. So that is actually doing a pretty good job. Also aligns well with our AA factor once we remove internal variability, also matching model. So it's pretty nice to hear that the force response is doing good. And then we can take monthly attributions of internal variability among these different methods. And so what I've done here is divided the associated estimate of internal variability by the total observed trends respective to the different methods. And there's good agreement between the CNN and the PI nudge methods for April and May. And these are two completely different methods. So that was really good to find. There is a difference in March, and I think there's a potential offset in warming and cooling trends that you see in PI nudge. They'll show up. There we go. So they are able to capture that negative sea level pressure anomaly trend that we saw in observations, which is great and why I wanted to use these. But I think that that's kind of persisting incoming warming trends through cyclonic rotation kind of on Northeast Siberia, but also pulling down cool air to the North Atlantic and offsetting it in PI nudge. Versus my CNN is just looking at these maps of actually 20 north and poleward. So I'm not just singling in on 60 north and poleward and getting a zero trend there. Okay, so my takeaways here. In our observations, we quantified internal variability in the spring mean. And so if you do that same, attribution of how much internal variability has contributed to spring mean AA is about 27% in the spring with up to 40% in April alone. And this is supported by independent CNN, I also did a dynamical adjustment to check this number and the wind nudge methods. So 3 completely different methods. When we remove internal variability, we reconcile that difference between modeled and observed springtime AA. And then we have these really high pattern correlations between the difference and the wind nudge simulation, showing us that 1, it's wind driven, but 2, we can have confidence in our forced Arctic warming pattern. I think that's all. Was
So
a
I think
little
we have,
long.
it's okay. I think we have time for one question or two if they're quick. Anyone in the room? Online? David?
Hey Scott, this is really cool to see and really well put together. I was wondering, like, what should we do next based on this?
Yeah, I see these are all 1, 2. These are number 1, 2, 3. Yeah, so there was more work on this where we showed that models can simulate the relationship between those 2 critical regions of sea level pressure and surface air temperature, but it's just really low in magnitude, which I think can come from the wind. So we've been phrasing it as like, we can turn up the internal variability, but we've identified exactly where it should be. But if you get the winds in there, I think you can start getting the warming pattern correct, which will be super important for prediction purposes since we're missing so much of that in the springtime.
All right. Well, our next speaker, thank you so much, guys. Our next speaker is online. Are you able to share your screen, Zia?
Yes. Can you see my screen?
You can see it. It's not in presenter. Yeah. Okay. I think that'll
Is
be
it
good.
you
We
now?
can see it and we can hear you. I'm going to mute us for now and I'll unmute us at the end.
Okay, great. Yeah. Good morning, everyone. So I'm still recovering from a cold, so I might cough, making noise during this presentation. Sorry for that. So for those who don't know me, I'm Xia. I'm currently a postdoc at UCLA, working with Jasper Kok, Ian, and Amado. And today I'm gonna share some of our preliminary results for the project that I have been working on here. So the idea is mainly using the CSM simulations to explore several cloud-based radiation management strategies focusing the polar regions, the Arctic region. So the cloud seeding has been proposed as a potential strategy for the Earth's radiation management or climate intervention if you prefer. So for all types of clouds, if we can classify them by their cloud phase, we have those warm clouds, ice clouds, and mixed phase clouds. And for each of them, there is a strategy proposed to seed these different types of clouds and hopefully to manage the radiation and cool the Earth. For example, for the liquid clouds, we have those so-called marine cloud brightening. The idea some of you might be familiar is to seed aerosols into those marine low-level clouds and to mimic those ship track to induce the cloud brightening, mainly through those TUMI effect. And for the ice clouds, and we have those serious cloud thinning strategy. So for this one, we hopefully to seeding the ice nucleation particles into those high-level series, and with the goal to stimulate the earlier ice nucleation and hopefully a cloud thinning, so you can allow more infrared radiation escape to the space from the Earth. And for mixed phase clouds, and this is a relatively new, but people have proposed those mixed phase cloud thinning strategy. So it's similar to the marine, the serious cloud thinning, except the ice nucleation particles is hoped to enhance the glaciation in the mixed phase clouds and also allow more the long wave escape to the space. And so our project focusing more on those relatively new mixed phase called thinning strategy. And but for so speaking of the Arctic radiation management, because of the many uniqueness of those polar region, we can either do the what I call short wave focused strategy during summer, such as marine cloud brightening, or the long wave focused strategy during the winter season, for example, mixed phase cloud thinning. So we're interested for these two contrasting cloud-based strategies, specifically marine cloud brightening and mixed phase cloud thinning. And specifically, we're interested in how do those two strategies compare in terms of their effects on mitigating the Arctic warming and also stabilizing the CS. So instead of manipulating the clouds and the aerosols in the model, giving there's uncertainties for not only clouds but also cloud aerosol interaction, and also sky also presented this Arctic climate also have uncertainty in the model. What we do is rather use a simplified way to represent the effects from this cloud seeding. So long story short, for the marine cloud brightening, once the clouds are brightening after the seeding, what this at the surface, what we can almost immediately notify is a reduction of the downwelling short wave. And similarly for the mixed phase cloud thinning, and the surface can pretty quickly pale a reduction of the long wave downward flux reaching the surface. So what we do is put perturbation for those downwelling radiation fluxes that are both going to the surface energy budget and affect your surface temperature and CS state. So to start with, we applied -10 watts per square meter into our study domain, which is everywhere covered by those blue area and north of the city or non-land area. And in 3 scenarios, one is only in winter for long wave downwelling perturbation to mimic the mixed phase cloud thinning, and one is only in summer for the short wave downwelling component, and also a combined strategy to mimic the combined mixed phase cloud thinning and marine cloud brightening. Sorry. So here, what I'm showing here, there's a lot, but I'm gonna walk you through this. This is looking at the temperature response for the zonal mean from the 3 experiments, and this is their seasonal cycle for the Arctic mean temperature response. So what you can tell here is we see Arctic confined temperature response mostly happening north of the 60, where we applied the first thing, and compared to those two strategies, red is the short wave forcing perturbation, and blue is the long wave. We see a slightly larger temperature response in the long wave forcing experiment. And outside of the forcing applied domain, you see slightly response in the northern hemisphere, in lower latitudes, not very limited in other hemisphere. And if we look at the combined strategy, which is the purple, and compared to the sum of those two individual responses, we see quite a linear response for the system. And those cooling are mostly occurring in winter season, especially from November all the way to March. And most of those cooling are happening, you see, over those coastal regions. So for CS response, similarly, we see only the notable response in the Arctic domain, and not too much going on in the Antarctic. Unlike the temperature, we see a slightly stronger shortwave forcing, CS response in the shortwave forcing compared to the longwave forcing, and most also similarly no matter what kind of forcing you have in which season, they all exhibit a quite robust seasonal response, where you see largest response in the fall season. And for the spatial map, what we can tell is those CS response largely happening over the region, in the coastal region, where we have those notable temperature response. So part of the reason that caused those cooling is due to the forcing, and another part is due to the different feedback process in the Arctic region. Here I'm showing those annual mean feedbacks for different processes, and what you can tell is for the largest two positive contribution is the albedo feedback and the lapse rate feedback, and each of them contribute roughly half of the total feedback process. And this is easy or straightforward to understand because we have a CS expansion in those forcing experiments, so that induce those albedo feedback and of course amplified the system cooling, and also because of the system cools and surface cools and the CS expands, we notice a very strong enhanced surface temperature inverting over the entire Arctic region, so that contributed to the lapse rate feedback. But what partially offsets this cooling is this called shortwave feedback. And it's the main negative feedback that damping the cooling, and is the main reason for this is called thinning, which we'll refer back later. But if we compare the magnitude of the feedbacks in the long wave forcing experiment versus the short wave, we notice more than double the short wave called feedback in those short wave cases compared to the long wave cases. And that partially explain why we notice slightly less temperature cooling in the short wave response. So the clouds represent negative short wave feedback, and if we see the cloud fraction, we don't see too much response in the cloud fraction, very limited reduction. However, the cloud liquid path, the cloud optic depth decreased, especially for the cloud water path. Here I'm overlapping the liquid path on top of this CS concentration response in the three experiments. And you see the dashed line gives you a negative response in LWP. What you can notice is a stronger reduction in the summer forcing experiment, and we see up to 20 gram per square meter reduction in this, and it's quite well co-located with the CS response as well. Wherever you see the CS expansion, you see this reduction in the liquid path from the clouds. One reason for those cloud thinning, what we figured out is the cooling surprised the hydrological system. The entire system is observed to slow down. So this is give you just one example for the zonal mean temperature, specific humidity, the P minus E, and then meridional moisture transport. And the right column is the response from one experiment, which is the long wave winter forcing experiment. So if we focus on the region over the Arctic north of 60, we see a cooling. And then we also notice the atmosphere has a small capacity to hold the moisture, and also reduced surface evaporation due to the recovery or expansion of your CS, and also much less reduction in the precipitation. That's where you see a negative P minus E. And also for the long range, large scale moisture transferred from the lower latitude, we also see a reduction in the for the moisture transporting into the high latitude region. So to summarize what I've just shared with you, we use the CSM simulations with idealized surface downwind forcing perturbation. And we notice the winter long wave focus radiation perturbation experiment produced slightly stronger Arctic cooling, but a slightly weaker CS recovery, and then the summer forcing. And these cooling differences arise from two main reasons. And part of the reason I didn't mention before, but part of the reason is the downwind shortwave forcing is reflected by the sea ice, while the downwind and long-wave forcing is almost all observed by your sea ice. And the second one is the emergency of the negative shortwave feedback after applying the forcing, and it's slightly stronger in this summer forcing experiment than the long-wave winter forcing experiment. And this identified negative shortwave forcing might suggest potential hidden pathways, which would have implications for Arctic radiation management strategies, such as marine cloud brightening and mixed physical thinning. I think, yeah, I will stop here and answer any questions you might have.
All right. Do we have any questions for Gia? Alec?
Yeah, thanks. Interesting talk. I was wondering if you've potentially looked at kind of analogs of maybe runs where you had similar, more extensive sea ice, and what the kind of hydrological cycle looked like in those states, to see if, you know, this is inducing kind of similar prior states, or if it's completely unrelated to what we've seen before in terms of like the hydrological cycle. If that makes any sense.
So if I understand correctly, you are talking about the sensitivity of this response to the mean state of the CS coverage in CSM. Is that right?
Well, yeah, I'm aware these are like idealized simulations, but like, is this kind of change in the hydrological cycle what we think has happened in recent decades? And, you know, is returning sea ice to a prior state going to somehow be similar to what the hydrological cycle looked like, or are those things completely separate? Is there any, you know?
Yeah, I have to check, comparison of those hydrological cycle to the current or future state of the CS. But related, what I can tell you is for those experiments, this CS data we started with is from pre-industry. So which means that we have quite a bit CS coverage compared to the future state or even the current state. For example, I'm showing here is the CS extent in the annual mean, and the green represented this control state, and the blue and the red represent after we impose the forcing, what the CS stage would be. So you can tell here I'm comparing to two data sets. One is the dashed line is from the NISIDC, and the black thick line is actually the prescribed CS condition to the AMIP, standard AMIP simulations used by CESM2. Nevertheless, you see those states CS cover extended in our model represents quite a large CS extent, roughly representing the 18th CS extent. So that means we started with a very extensive CS extent. The hydrological cycle might be different from the future or current. Mm-hmm. Hopefully answers your question.
Okay, thank you so much. I think we're going to move on to the next talk. Molly is going to join. You'll have to stop sharing your screen. Yeah.
Oh yeah. Wait for a sec.
I know it's very I find it Google.
There are like multiple buttons.
Yeah.
Just the last one.
We'll continue on the theme of modifying the environment in different ways.
Yes. Okay. So, for those of you that do not know me, or that I haven't met yet, I'm Molly. I'm a postdoc in the ASP program here at NCAR. And yes, we're continuing on the theme of kind of climate intervention, and models. And we're deviating a little bit, and talking specifically about climate interventions that interact with sea ice specifically. And before I want to get into it, I want to say first, this is going to be kind of a high level talk because I tried it with a lot of detail. And even when I was talking to myself, it was 45 minutes long. And then also, I just want to acknowledge off the bat that climate intervention is a kind of complex research topic that challenges a lot of things at the intersection of climate change and ethics and the scientific method. And so a lot of those things are not in this talk. We're focusing very specifically on the idea of model suitability for studying a specific intervention. I want to thank Ed and Marika, who have been kind of contributing to this work, and then also acknowledge that a lot of it has evolved with very specific help from David Clemens-Sewell, CC Bitts, and Dave Bailey. So to just kick us straight off the bat, if you are not familiar, Arctic ice management is an idea that proposes you could slow Arctic sea ice loss by intentionally flooding the sea ice surface of the Arctic in the wintertime. And we'll walk through schematically what this looks like by just first looking at what normal sea ice evolution looks like over the course of a year in the Arctic in a primarily thermodynamic environment. So in this kind of setup in the wintertime, sea ice is growing primarily due to congelation growth at the bottom because you're conducting heat from the warmer ocean to the very cold Arctic atmosphere through the sea ice, which supercools the water below the ice and forms new ice on the bottom. This effect is really strongly modulated by the presence of snow on top of the sea ice, which is more insulative than the ice itself, and so reduces the overall thermal conductivity of the column. And then in the spring and summer, when you get increasing insulation and rising temperatures, you start melting. And if your ice isn't thick enough, you should expose kind of quite a bit of open ocean by the time you get to the peak of the summer season, and you lose all of your brighter snow. So the overall albedo of the system decreases. The idea behind AIM, Arctic ice management, is really that if you were to pump seawater from underneath the sea ice surface, or underneath the sea ice onto the sea ice surface, during the winter, you would have kind of a double thickening effect. First, because you're exposing that pumped seawater on the surface to very cold atmosphere, and it should freeze pretty quickly. But then also by doing that, you are saturating and removing the snow layer. So you're increasing the overall thermal conductivity of the column relative to normal conditions, which should enhance your rate of congelation growth at the bottom. The idea is that if you do enough of this thickening, you introduce kind of an increased resistance to melt in the spring and summer, and potentially keep more of your Arctic sea ice cover, thereby increasing the overall albedo of the system relative to normal conditions. So this idea was kind of first proposed in 1997 and then popularized perhaps by a study in 2017 that used a freezing degree day model to estimate approximately how much thickening you might be able to get if you applied this in the Arctic. And then from there, it was adopted in a couple of coupled climate model simulations that applied it at large scale using different representations of the flooding to try to get a sense of what the Arctic and global climate response might be to this. Those studies, there are just two of them. I'm not going to go into them in depth. If you have questions, I'm happy to talk more about them later. CC is also a co-author on one of them and has very specific familiarity with it. But the two studies did kind of jointly find that there was a multi-decadal slowdown in sea ice loss as a result of applying their representations of flooding, and that there was no global mean temperature response to this kind of intervention in those simulations. The other thing that those studies have in common is that there's no way to evaluate them. There are no analogs or deployments of this at scale such that you could understand whether they are kind of accurately representing what would happen in the real world. But nonetheless, the idea kind of migrated outside of academic settings, and there are now privately and publicly funded field tests that have emerged in the Arctic in the last 10 years or so. The first of which was from this company called Realize, which is based in the UK, and ran their first field test in Nome, Alaska in 2023. And then in kind of an ongoing fashion, they've been operating in Cambridge and Nunavut since 2024. Pretty simultaneously, there's another company known as Arctic Reflections, which is based out of the Netherlands, and they've been running field tests sequentially on Svalbard in 2024, in Pistolet Bay in Newfoundland 2025, and then beginning this year in Tikkatarjuaq, Nunavut. Thank you. I spent a lot of time practicing that one. These two field tests are running pretty similar operations and generating pretty similar data. On the one hand, these are field tests that are providing us observations about what this looks like in the field. On the other hand, practically and conceptually, doing this at this scale in the real world is very different than what was being represented in coupled climate model simulations. And so there are a lot of questions that come out of that, both kind of progress from coupled climate simulations to field tests, and then what the field tests might tell us about the coupled climate model simulations. And some of the things that come out of this for me directly are this set of questions, which is first, are our current sea ice model components that were in the coupled climate model simulations fit for purpose? Are they suitable tools for researching this process? And then, given that we know that a lot of our models fall short in some ways, in what ways do those models maybe fall short for this specific process? And what might simulations of these field studies imply for ongoing attempts to look at this in the field? So we'll start getting at some of these questions by specifically trying to apply a local modeling framework to the field test that occurred in the 2024-2025 season in Cambridge Bay. And as a very brief overview of that field test, this is some schematic of what it looks like to do this up there. So the field test happened on the southern end of Victoria Island in a mostly enclosed bay. So we're thinking about this as a primarily thermodynamic sea ice environment with periodic flooding over the course of a November to March field season in this 1 kilometer by 1 kilometer research area that I'm kind of illustrating schematically on the left. The colors simply represent the months in which the different research subsites were flooded within the 1 kilometer research area. And you'll note that there are 3 sites that were not flooded and were withheld as control sites. The flooding happens by installing a pump through the sea ice. The pump is connected to an output hose or an output pipe with a hose and secured by a cofferdam, which both supports the whole structure and prevents backflow of the flooded water through the hole back into the ocean. In the realized case, these pumps are powered electrically, so it requires bringing a battery out there, and the batteries have a lifetime of about 4 hours. So they were able to flood each day that they brought the pumps out for anywhere between 4 and 8 hours, depending on the availability of people power to go out and replace the batteries. And coincident with the pumping, the field team took a number of observations at each of these research sites, including ice thickness, snow depth. They did some coring to try to get an idea about salinity profiles. And then at a subset of the flooding sites, R3, R4, and R7, and then at one control site, they installed SIMBA thermistor chains, which take vertical temperature measurements from the upper atmosphere through the ice down to the upper ocean, or the lower atmosphere, excuse me. So we have this field site. We have some data about what happened, both in terms of the implementation and in terms of the observed environment, and we want to try to model it. So we developed a kind of local modeling framework that is based around IcePack, which I'm assuming most people online in this room are familiar with, but if you're not, it is the column physics package of the SICE sea ice model. To get IcePack to represent what was happening at this specific location, we forced it with atmospheric conditions from the Cambridge Bay Shore Station, which is a weather station relatively near to the research site. The only variable we couldn't get from that research station was radiative fluxes, which come from an hourly synoptic scale series product. We coupled IcePack to a slab ocean and ran it or initialized it with information from the Cambridge Bay Underwater Network, which is an underwater measuring platform also relatively close to the research site. And then variables we couldn't get from that, we took from the ocean reanalysis system. The model is set up to run with a single sea ice category. It has 8 vertical ice layers and 3 vertical snow layers. We use Delta Eddington radiation, the mushy thermodynamic scheme, and the sea level ponds parameterization that you heard about from David yesterday. Most of the nameless parameters we kept as the recommended defaults, with the exception of a couple that we tweaked in response to conversations with people that know a lot more about them than I do. And to represent the flooding, we used an updated version of the flooding scheme that was used in the coupled climate simulation run by Pauling and Bitts, which prescribes a flooding rate in meters per hour and uses the existing snow ice formation module in the ice pack code to represent subsequent freezing of a saturated snow layer. To initialize the model in terms of ice and snow, we used the real ice in situ observations from the field, and then prescribed the pumping rates based on their pumping data. The simulations that come out of this, we compare to the field measurements of ice thickness and snow depth, as well as some estimated melt rates from the field. We did comparisons against salinity profiles from the ice cores and against drone-based luminous estimates as a proxy for albedo. And then to kind of contextualize both the observations from the field and the simulations, we were able to compare to a wintertime sea ice thickness record that's been maintained in Cambridge Bay since 2003. Okay, so this is our modeling framework. We run a bunch of simulations. This is the initial result from the subset of simulations that we ran. So I'm showing you the results in terms of ice thickness on the y-axis for the kind of representative field season, December through the melt out in August. On each of these plots, the scatter points represent the observations that were taken in the field with some measurement of daily, or some estimate of daily measurement uncertainty. The blue lines represent the control simulations that came out of IcePack, and the solid colored lines represent the model simulations that had representations of flooding in them. Other things on this plot that we need to think about, in the background, the gray envelope represents the historical wintertime sea ice thickness record at Cambridge Bay, where the envelope is the standard deviation of anomalies around the detrended annual cycle. Pretty reasonably, there are no springtime thickness estimates from Cambridge Bay because people don't really want to go out on the melting ice. And so I've estimated what the melt out range might look like. It's a little bit difficult to see, but it's stippling in the melt season in the background based on observed melt rates. Things that kind of stand out immediately from this, you can see that the flooding simulations and the colored lines do a pretty good job representing the observed jump in sea ice thickness at the time of flooding, which is great. And then when we compare those flooding simulations to independent thickness estimates based on the SIMBA temperature profile data, there's a very small centimeter scale RMSE between those observed estimates of thickness and the model simulations. So those two things taken together, we can make a kind of first broad statement that in terms of suitability for purpose or fitness for purpose, IcePack is probably a pretty good tool at representing ice growth as a result of flooding. However, the other thing on this figure that I haven't talked about yet are these two little boxes in the R4 and R7 sites, which represents a qualitative estimate of how the ice was thinning during the melt season in the field. So this is based on observations that were taken when researchers went out in the field to collect the permanent SIMBA installments when they were melting out of the ice. And what the field team noticed is that the ice at that point was anywhere between 40 centimeters to over a meter thick in this kind of week-long window in which they were collecting these instruments. And what you'll notice is that in both the control and the flooded simulations, the model is overestimating sea ice thickness compared to those kind of qualitative observations at this period of time. And so we should first acknowledge that this is giving us kind of an idea that our model might not be good for this particular purpose of understanding kind of the melt period that's occurring in the field, both in terms of just melt in general, whether you're talking about flooding or control, and then also the flooding simulations are overestimated as well. But the thing that we can do from that is then start to investigate why this mismatch might exist. And so to do that, we started by comparing observed melt rates to the modeled melt rates. So melt rate on the y-axis, time on the x-axis. The gray shaded region represents the period in which we have both observations and modeled melt rates. And the thing that I want to point out kind of right away off the bat is that the obs are in general melting faster than the model. And then specifically, and a little bit more difficult to pull out, is that the flooded sites in the observations melt less quickly than the control sites. But that pattern does not exist in the models, where the melt rates are pretty identical, regardless of whether or not you've applied flooding or not. So to dig into this a little bit further, we looked at the relative albedo in the model simulations, in flooded simulations compared to control simulations, which is what I'm showing here. The metric on the y-axis is the albedo in the flooded sites divided by the albedo in the control sites. And to kind of walk you through it, in this period of time, which is after flooding has stopped, but in a period in which we're still growing sea ice and we still have snow on top of the sea ice, the relative albedo is about 90%, which makes sense because the flooding has eroded some of the snow layer in the flooded sites, so it's a little less bright in those sites. But then when we get to the ice melt period, you'll note that in the model, both the flooded sites and the control sites have a pretty similar albedo estimate. Given that we're applying the same atmospheric forcing and the albedo is kind of coming from the Delta Eddington scheme, we looked at some of the ways in which the sea ice modifies that estimate of albedo. And the first place that we looked was kind of at the melt ponds. But the reason that we were really motivated to do this is if you look at relative luminance observations from the field, acknowledging that luminance and albedo are different metrics, but we should expect their relative relationship to behave somewhat similarly. There's a pretty significant mismatch between what the model is representing in terms of how bright these sites are and what the observations are telling us about how bright they are. And in particular, we looked at the melt ponds in order to understand some of the model patterns. And in this spike in which the flooded sites appear brighter than the control sites, the flooded sites have fewer melt ponds or a smaller areal fraction of melt ponds than the control sites do. But in this period in which we have similar albedos, the melt pond fractions are pretty similar between the flooded sites and the control sites in the model. Qualitatively, this kind of disagrees with what's being observed in the field. So these are drone images during the melt period taken at the research site in Cambridge Bay. And you'll note that by the time we get to May 29th and melt has begun in earnest, the research sites that were flooded are brighter than the control sites that were not flooded and appear to have a much smaller melt pond fraction. This pattern kind of continues throughout the melt season, where now we're looking at a sentinel image because I had to kind of take what I could find. And you'll note that, again, the research sites are brighter and appear to have a smaller contribution from melt ponds compared to this control site up on the upper left. So current takeaways, because I'm sure I'm running a little bit over. There are a lot of analyses that come out of these simulations that we're not talking about today, but in terms of the analysis pathway that we have taken, the things that we might surmise are that ice pack is probably fit for purpose if you want to understand how ice growth is occurring in response to flooding at this local scale. But there are a lot of issues if you're trying to think about its utility for understanding the melt season. And that has implications on whether or not you would use this tool to predict the ice-free date. And some of that comes because the model representations of albedo differ from the observations when you compare flooded sites to control sites. And this is maybe related to what's happening with melt pond evolution in the models. Some recommendations that I would give to the field team based on this are mostly just that it would be really nice to have direct albedo and surface radiative measurements from the research sites, as well as direct observations of the melt pond evolution in terms of area and depth. And with that, the next direction that we're kind of thinking about for this is all of this is considering whether or not the model is a good tool in terms of this one specific instance. But if we wanted to kind of move in the direction of understanding how larger model simulations inform this idea, we would want to understand more of a contextual fitness for purpose. And so the immediate next step for that is to try to take this analysis and apply it to the Arctic reflections field sites, which have similar methodology and similar data coming from them. So that's it for today. But if you are curious about this and want to talk about it, I'm having a lot of fun with this project. It's got a lot of dimensions to it and I would love to chat. So let me know.
Maybe one question while I switch out the slides and the group that's coming. I don't know if you all want to here. Yeah, a question. Any questions? Sky.
Yeah, you mentioned that you want depth measurements.
Yeah.
On observations. Have you looked at what the depth is in the models later in the melt?
Yeah, so not only, so the area, in terms of flooded versus control sites, the areal fraction of melt ponds is pretty similar in that melt period, but the depth from the flooded sites is actually 20 to 40% greater in the flooded sites than in the controls. So you can get that from the model, which tracks volume and area for the ponds, but yeah.
Laptop.
Okay. So I know we're running a little behind. We're still gonna have a full break, and I'm just shifting the post-break schedule a little bit. The next talk, again, environmental modification, and unusually, so it's going to be a 30-minute talk, but there are 4 people presenting. And so we're going to cycle through Walker, who is right here, Claire, who's online, and then David and Courtney. And I'm assuming you guys will figure out your timing within that, but we do want to be at 10:15. We want to make sure we have a break. So
Understood. So,
Okay.
Good morning, everybody. Like we heard, going to be presenting on a group project today. So we're talking about marine cloud brightening interventions simulated in CESM2 in the Arctic system and beyond. So this is a project in collaboration with the University of Colorado, funded by the Grantham Foundation. Andrew and Marika are our PIs. The 4 of us are all scientists on the project, and we're going to be taking turns talking today. Laura and Aaron also joined us recently. And then lastly, we want to acknowledge a number of collaborators at NCAR and beyond, including Xia, who presented earlier. So I'm going to start by talking about the motivation for the project, our experimental setup, and what this kind of intervention could reasonably be expected to do to the planet model. And then Claire and David and Courtney are going to talk about the remaining preliminary findings from our experiments. So I'm going to be talking about climate intervention. It can go by a variety of names. Solar radiation modification, solar geoengineering. Basically, it refers to families of proposed technologies which would cool the planet by modifying the Earth's radiation streams with the intention of cooling the planet and reducing some of the impacts of global warming. And today I'm going to be focusing specifically on marine cloud brightening, increasing the Earth's albedo by increasing the reflectivity of marine clouds, abbreviated MCB. And I also just want to echo everything that Molly said, that any kind of proposed climate intervention is going to have serious political, governance, and ethical concerns. Today we're focusing on the natural science, but I do want to just acknowledge that those exist. And for every person like me who's working on the physical science, there's probably somebody else working on the social science. So how marine cloud brightening works is the idea is that by spraying aerosols, probably sea salt, into the lower marine boundary layer, those sea salt aerosols would act as cloud condensation nuclei, allowing more water droplets to form and increasing the optical thickness of the cloud. This is called the Toomey effect. But marine cloud brightening could also influence the lifetimes of low marine clouds, and there would also be direct radiative effects from the spraying of the aerosols. And the purpose of this project is to see what a marine cloud brightening intervention in the Arctic would look like in CESM2. Could a marine cloud brightening intervention preserve aspects of the Arctic climate like sea ice, and what would the effects be outside of the Arctic? So in order to explore that possibility, we're running the fully coupled model, CESM2, with CAM6 as the atmospheric component. We're running a future warming scenario called SSP 370. We're running the model for model years 2035 to 2070. So this is a 35-year simulation in the near future, and it also is the same timeline as other recent prominent climate intervention scenarios. So that leaves the door open for comparison if we want to go down that avenue. We have some modifications to the model since the CMIP6 configuration. Firstly, we're using the smooth biomass burning at the end of the historical period. And then we're running what is called the less melt configuration, which are mods to indirectly increase sea ice albedo and bring sea ice behavior in the model more in line with observations. And then we have additional ocean biogeochemistry representation called 4P2Z, which lets us look at some of the ecosystem impacts in the model, which Courtney's going to talk about later. So we have 5 baseline ensemble members of this CESM2 configuration. And then on top of that, we're running 9 MCB simulations. And the way that we implement MCB in this model is we perturb ND, which is the cloud droplet number concentration, usually measured in number of liquid cloud droplets per cubic centimeter, in low clouds in select grid cells to artificially replicate the brightening effect that we would expect to see from marine cloud brightening. So which grid cells? We're, like I said, we're focusing on the Arctic, and we have 3 different seeding maps that we're comparing. The first one, we're just calling annual or year-round seeding. All grid cells inside of the Arctic Circle, represented by this green patch here, we're increasing the brightness of low clouds everywhere inside the Arctic Circle. Doesn't matter whether it's over land or over ocean, and we're doing it in all months of the year. The next strategy is summer only. In the months of May through September, we're perturbing clouds in the same region for reasons that Xia touched on in her talk, and Claire is going to talk about next. We're increasing the brightness of clouds only in the months of May through September, and we're not doing any interventions in the winter months of October through April. And then the last strategy that we have is the most complicated. We're calling it the dynamic mask. We're still only seeding in the summer and only in the Arctic Circle, but this time we're focusing on the grid cells that are mostly ocean. We're excluding grid cells that are land and also those that are completely covered in sea ice. And the model checks every time step to determine whether or not to seed those clouds. And on average, the masks look something like this, with the dark green regions representing regions that are being seeded most or all of the time, and light green or white regions are those being seeded less often. And so for each of these strategies, we're simulating 3 different interventions, low, moderate, and high intensity, with MD set to either 100, 200, or 400 droplets per cubic centimeter. And so the 3 strategies times 3 different perturbation strengths per strategy is how we get to 9 different simulations. So one more slide from me before I hand it over to Claire. How much does this kind of intervention cool the planet in CESM2? Looking at a representative sample, the dynamic mask medium strength intervention is kind of the median in terms of how much we cool the planet. CESM2 shows that this would cool the Arctic by about 2 to 3 degrees on average. And while the intervention is confined to the Arctic, the effects are not. You would expect to see cooling over land in most of the Northern Hemisphere by doing this kind of intervention. And additionally, because we're perturbing the pattern of the Earth's energy fluxes, by cooling the Northern Hemisphere only, we would reasonably expect to push the ITCZ towards the Southern Hemisphere, which is a pretty robust result that we see in climate intervention simulations. This could or could not be a bad thing, but I just wanted to demonstrate in one figure how a climate intervention inside the Arctic could have far-reaching effects outside of the Arctic. Similarly, if we plot the strength of the Atlantic Meridional Overturning Circulation, or AMOC, by cooling the high latitudes in the Northern Hemisphere, we would reasonably expect to increase the strength of the AMOC, which we see in all 3 of our dynamic mask simulations, with the strongest perturbation having the strongest impact. So this, again, that may or may not be a good thing or a bad thing, but it's an example of a kind of effect you would see from this intervention outside the Arctic. And with that, I'm going to throw it over to Claire.
Okay, great. You all can hear me. You'll shout if not. And Walker, please, will be advancing the slides for me. So, hi everyone. I'm Claire Singer, and I am going to be focusing on the kind of atmospheric and surface energy budget perspective of these different intervention strategies. So on the next slide, I want to just give us a bit more background about how clouds are controlling the surface energy budget in the Arctic in the unperturbed control scenario. So this is still from CSM2. This is from our control experiments. And on the left here, I'm plotting the surface cloud radiative effect. So the difference in the surface energy budget when we have clouds versus clear sky. And so you can see that in from the long wave perspective, the presence of clouds is always warming the surface. And from the short wave perspective, when there is insolation, clouds are strongly cooling the surface. And so this leads to this very large seasonal cycle where the presence of clouds is really only cooling the Arctic surface in the summer. And if we look at that more regionally in the maps, you can see that even, say, in the month of June, when there is strong cooling by clouds of the surface kind of averaged over the entire Arctic, this is predominantly happening outside of the sea ice region. So this green contour is showing, I think, the 50% sea ice concentration contour. And so even over the sea ice itself, the clouds are still having a slight warming effect because basically sea ice is already so reflective that the long wave effect of the clouds is kind of dominating. And so this is a little bit different from thinking about how brightening or thickening these clouds will change the surface energy budget, but it gives us a pretty baseline for what we could expect. And this is kind of how we came up with these different intervention strategies that Walker just explained. So on the next slide, we'll jump into some results. So here I'm showing the difference from each perturbation run minus the control ensemble. So in panel A, this is the change in the Arctic sea ice area. You can see that all of these interventions increase the sea ice area, mostly in the summer and fall season. In panel B, this is the change in surface air temperature. So for the most part, we see a cooling in the annual intervention strategies, especially for the smaller magnitude interventions. We see a little bit of warming in the winter. So that's because of this long wave effect of thickening the clouds. And so by doing the intervention just in the summer, which is shown in these dashed and dotted curves, we see that we can eliminate that unwanted winter warming. And then on the bottom, I'm showing the short wave and long wave cloud radiative effect at the surface. So thickening the clouds in the short wave, we would expect that this would enhance the shortwave CRE, so make it more negative. And that's what we see in the springtime. But in the summertime, we actually see the opposite. And that's because the cloud radiative effect it's the difference between when we do have clouds and when we don't have clouds, and the surface cover itself, or the surface albedo itself, actually has an influence, as well as the change in the cloud properties. So if you click one time, maybe a little pop-up. Yeah, so the brighter surface from enhancing the sea ice coverage is actually making the shortwave CRE less negative. And that's kind of totally consistent. And we see kind of the same thing in the long wave as well, from the enhanced cooling that we get in the fall season. Okay, the next slide. Here I'm showing changes in the cloud and precipitation itself. So the cloud water path increases substantially. So this is kind of that lifetime effect that Walker mentioned. So we've increased the number of droplets, that decreases their sizes. The clouds stick around for longer, and there's more water in them. Pretty much that is entirely happening in the liquid phase. And that's kind of a good sanity check for us, that we're trying to just perturb the liquid phase. These clouds do have some ice in them. We're not really messing with the ice when we do this perturbation, and that's reassuring. There's not some weird microphysical feedbacks happening. In terms of the precipitation, we see in the summer this kind of shift of less rain and more snow, consistent with that cooling trend. In the fall, however, we see kind of a decrease in precipitation overall, less rain and less snow. And I think that's something still to dig a bit more into, whether that's kind of similar to what Xiao was seeing, if that's something about the local cooling, limiting the kind of local moisture supply from the atmosphere, if there's some component of transport there as well. On the next slide, across a number of different metrics that we look at, change in sea ice area, surface air temperature, aspects of the radiation and the cloud water path, the response that we're seeing is kind of largely linear per doubling of droplet number concentration. And so that is nice. It lets us kind of think about interpolating the strength of this perturbation to the strength of the intervention that we're applying. And then David's going to show a little bit of some aspects of the system that actually have a very nonlinear response. And then my last slide here. Yeah, so we can compare kind of the difference between the effect of this perturbation and what I'm calling the efficiency of the perturbation. So the effect being just how much more sea ice do we have in each of these perturbed experiments, whereas the efficiency I'm defining here is the change in the Arctic sea ice area divided by the kind of total amount of perturbation that we're doing. So the area that we're perturbing, as well as the magnitude of that perturbation in terms of the droplet number concentration. If you click one more time, you can see that kind of the strategy with the biggest effect is this one with the largest magnitude of the droplet number change, where we just apply it in the summer, but everywhere, versus the one that's kind of most efficient is the one actually with the smallest droplet number perturbation, that's restricted to being just over the open water. And then I have some of those takeaways just summarized on the next slide. And I will pass it off to David and Courtney to tell us more about the sea ice and ecosystem responses. Thanks.
Awesome. Thank you, Claire and Walker. Good morning, everyone. So I'm going to focus on the snow, sea ice, and upper ocean impacts. And Alex's question actually sort of set the stage for this, but we implicitly, when we talk about these type of climate perturbations, we think about returning to a past Arctic state. And these plots of the key state variables, ice area on the upper left, Northern Hemisphere ice volume, and Northern Hemisphere snow volume at the bottom, are sort of showing why we would think that, why we'd want to do that. So this is looking at the control run with no perturbation going all the way back to the 1920s. And you can see in the past there was more ice, particularly in the summer, and it was thicker. And if we look at the just in terms of ice area, we see that the perturbations do indeed return us to a seasonal cycle that looks like the past, or at least the past in CSM2. We see a similar story in ice volume, although if you look closely there, you will notice that the seasonal cycle is dampened, which means that there is less growth, and less melt for a given mean ice thickness. But now if we look at the snow volume, we see a very, very different response. And so particularly the larger perturbations here, the 200 and 400, have the potential to produce unprecedented perennial snowpacks. For this, the remainder of our talk, both myself and Courtney, we're not going to show any results from the annual simulations, just for the reasons that Claire gave earlier. And so just to highlight again how exceptional these snow conditions are on the sea ice, this plot is showing in 2 dimensions the distribution of September ice thickness on the x-axis and snow depth on the y-axis, averaged across the entire Arctic. The colored blobs at the bottom are all showing 90th percentile contours for different decades in the control. And you can clearly see that for the summer full Arctic perturbations, as well as the strongest dynamic mass perturbation, we have just dramatically different snow states in September. We have snow that's unlike anything in the historical record in CSM2 or in the historical record in observations. And so I've talked about what's happening. Very briefly, I want to discuss why it's happening. And the short version is that snowmelt and albedo changes are part of a positive feedback cycle. And by perturbing the incoming solar radiation, we are basically interrupting that positive feedback cycle. I should highlight, I don't think there's anything terribly special about marine cloud brightening versus other solar radiation managing. I think we could see this mechanism happening in all manner of potential perturbations. Interrupting this positive feedback cycle has direct impacts of causing more snow and more ice. It will also indirectly have impacts on the light availability for primary productivity and cause changes in our ocean stratification. And so just to sort of walk through that mechanism a little bit more, I'm going to show an example of what happens to sort of the key ice variables and fluxes in the first year that we initiate this perturbation. These green lines here are showing essentially my mouse has vanished, sorry. These green lines here are showing the normal progression. So seasonally, the melt season starts with, sorry, everyone, slight technical difficulties. I'll just point at the screen. The melt season starts with the seasonal rise of incoming solar radiation, which begins to peak in May and June. At about a month lag, this leads to a peak in the snow melt rate, which more or less fully decreases ablates all of the snow from the Arctic sea ice. And then at another month lag, we see the ice surface melt, really kick into gear, which decreases our ice area and leads to sort of the classic melt season. The dashed orange line here is now showing what happens when we interrupt this cycle. So coming from the top, you know, we can see we've greatly reduced the incoming shortwave in May and June. That leads to, in this particular perturbation, about a halving of the snow melt rate, which means that by July, there's still snow melt. There's still snow on the surface of the ice. We don't get ice surface melt starting. I don't show this here, but we also don't get ponds forming. So you could think of this as sort of the Antarctification of the Arctic, if you would like. Having more snow at the end of the summer, plus having more ice to accumulate the first storms, leads to more snow throughout the year, which also leads to an interannual positive snow feedback. These changes don't just impact the snow and the ice, they also impact the upper ocean. In particular, in the central Arctic, we tend to see deeper mixed layers in these perturbed simulations, and we particularly see a deeper mixed layer in June, right at kind of the start of the growth season for the marine ecosystem, due to a delaying in the shoaling from the delayed ice melt. And then finally, I'll highlight that these changes also result in exceptionally low and unprecedentedly low levels of light availability in the upper ocean for the full summer runs. And Courtney, I think we'll pick it up there.
All right. So we'll move on to the most important part of the system now. So phytoplankton are the single-celled plants that live in the surface ocean and are maneuvered around by surface ocean currents. This is an image of a phytoplankton bloom off the coast of Norway and Russia, taken from a NOAA image. And phytoplankton are important for a couple of reasons. They, as David consistently highlighted, thank you, David, they're an important food source for the marine ecosystem. And they also are pretty important to the global carbon cycle. They take up and fix carbon in the surface ocean. And if they're not consumed, they can sink and sequester that carbon for long time scales in the deep ocean. So when we typically talk about phytoplankton, we think about this metric of net primary production, which is a metric of how much carbon is available for these important processes. In the Arctic, between 1920 and 2070, their net primary production rates averaged between 300 and 500 teragrams of carbon per year over our control simulations. However, this kind of long-term average masks some huge changes that had happened. Between 2035 and 2070, we see that productivity was really shifted to a much higher rate through the Arctic, between 400 and 550 teragrams of carbon per year. When we look instead at these dynamic mask experiments, you see that just like David showed with many of these, the lighter interventions kind of push us back into the historic envelope. We get conditions that look more like early 20th century, but the most extreme dynamic mask intervention results in kind of a slightly unprecedented rate of productivity. And when we consider the summer values, we see something really unprecedented, with the most extreme intervention resulting in a halving of the productivity in the Arctic. These perturbations overall are significantly reducing Arctic productivity. As David already highlighted, the reason behind that is essentially due to the changes in light. So this is similarly to the figures that David just showed us. This shows the kind of historic envelope in the yellow to green colors. And then each of the dots represents 1 year for the 2040s of each perturbation. And when we look at the relationship between light and productivity, we can see that an increase in light generally yields more productivity, and thus that the lower light conditions that we're seeing in some of these perturbations are resulting in a huge drop in productivity. Something else that's kind of interesting to note is that the relationship between light and productivity seems to be changing a little bit with these perturbations. You'll see that at the same light level, we're seeing an increase in productivity relative to what we saw in the baseline runs. And that's likely, as David alluded to, due to the changes in stratification that are resulting.
So another question we are curious about is where these impacts are greatest. So here's a map, a series of maps of these different experimental treatments. We have the summer on the left and the dynamic mask on the right, and an increase in the ND and the intensity as we go down both different rows. And for each of these experiments, I'm showing you the change in productivity relative to a 2040s baseline in percent space. And across all these, we can see that for the most part, the decline is focused in the central Arctic region, the same region that David highlighted with these large changes in light and snow. And the changes are pretty shocking. We see within the region north of 80 degrees north, 15 to 82% decline in productivity. Over the region that we're actually perturbing, the region north of 67 degrees north, we see up to 40% decline in productivity. And then even over this larger region that I'm showing you, 50 degrees north and up, there's a 3 to 10% decline in NPP, which is important because these areas host some of the world's largest fisheries. So there are likely some pretty big consequences. So overall, I found that these brightening perturbations can substantially dampen Arctic and subarctic phytoplankton production, and that those changes in productivity are largely tied to reductions in light, which, as David illustrated, are driven by the increase in snow thickness. And then I'm really curious to further understand how these reductions in productivity are likely to impact regional carbon sequestration, as well as food availability to marine ecosystems. So with that, thank you for your attention for this mega talk. And I'll leave our takeaways up here for questions.
All right, I think we have time for a question or two. Anyone?
I just had a quick one. I missed the motivation of the dynamic mask. Is that about deployment strategies?
Sort of a combination of deployment strategy and then also, as Claire
Do you
showed,
want to click back to my first slide?
yeah. The strongest cooling effect is over the ocean and not over the sea ice. So by sea, only over the ocean.
12. Yeah. Yeah, because the CRE is still slightly positive over the ice, even in like the month of June here. I don't know how well these colors show up for you guys, but it's like a little bit pink.
Right. Gotcha.
All right. Other questions?
So for Courtney, I noticed that a little bit further south in the Atlantic, you saw a slight increase in nitrogen productivity. But I mean, this is one thing we saw in the microplastics and everything, that when you change these things, mostly in the high latitude, that there are these effects elsewhere too. So I just wondered about that with the implications for fisheries, say.
Yeah, so there, you're right. There is an increase in some of the simulations in that area. That is probably due to the fact that there's all this unused nutrient, all these unused nutrients in the surface ocean that are kind of advecting downstream. And that could lead to small bumps in productivity in some kind of important areas. That was particularly true in the kind of Eastern Arctic. In the Western Arctic, there's a reduction downstream still.
Online, Shia, if you want to unmute and ask your question.
Yeah. So this is for Walker, maybe. I remember, I recall you proposed a 3 set of experiments. One is you call all, and then it's summer, and then it's dynamic. But I feel like maybe I'm wrong, but most of the analysis, I don't see the results from the all simulation. Is there a reason to to simulate that one, but you didn't check the results from that experiment? And for the summer versus the dynamic, the summer seems covering all the grades, right, including the land surface, versus the dynamic where you exclude the land mask. I'm thinking, comparing your summer versus the dynamic, are there any benefits to include the land, the perturbation over the land surface, if that makes sense?
Go ahead.
Sure. Yeah. Thanks, Shai. Yeah, I sort of glaze over that really quickly, but basically because of, so we have looked at all the simulations. But as Claire showed really nicely, like the annual are both less effective and also would be logistically very complicated. And so for Courtney and my talks, just to have fewer lines on the slides, we did not include showing the annual. They show generally similar effects to the summer full Arctic perturbation, but the changes are slightly smaller, generally speaking. And then the second part of your question was about introducing a perturbation over the land. We've taken a little bit of look at what this does over the land surface. I think there's reasons you could make an argument why one might want to do something like this. There is, for the most of the land in the Arctic is snow covered, and so you similarly have a snow albedo feedback that happens there. But we don't see, in sort of the very preliminary stuff we looked at, you don't get that much added bang for your buck if you do it over the land. So like Claire's kind of showing here, right? If you do it over the ocean, you get this added benefit because you can produce such a pronounced surface albedo shift, and you can't pull off nearly as strong of one over the land. Does that make sense?
Yeah, thanks. That helps a lot.
Okay. Is your question?
It was pretty
relatively
similar.
clear? Okay. All right. Well, thank you all for the mega talk, and we'll take a break. We'll come back here at 10:30. So we still want the full time to have a brain break and all that. And we'll just shift back the second half of the morning schedule. So we'll see you back here in 16 minutes.
Yes.
One of the culprits getting
Yes.
are like right.
Was that a verse or did they like happen?
Yes, that's a great question. Yeah. Great note.
I don't know how much they thought about it.
Yeah. So, yes, you're right. The observations are lying kind of in historical conditions. What's important to note is we detrended
Sure.
the Sea thickness annual study. So this is like an approximation of climatological conditions. And what's important about that is mostly like noting the control, like this here, which we talked to Ed about this. We did some analysis with Scott, like Allison, I don't know, I met her, but she's that identified like this was a particular warm winter in Cambridge Bay. And so the control conditions actually fall outside of our estimate of what.
Yeah, we're doing it
actually
slightly
falls.
dirty. I don't know exactly
Outside of an anthropogenic trend. You know better than anyone, this kind of approximation of internal variability and like natural background state is extremely approximate. But what's kind of neat is we were originally trying to figure out like, okay, so how much does flooding signal, why, like how much?
Right now, other models that we
And there's actually kind of a like interesting reverse
there's a marine
like,
flood
okay, your control is actually significantly below. It's like
Yes.
outside.
He's one of the early sort of pioneers. And he's an
I mean, I do
now,
too.
and they're doing some PSM experiments where they spray sea salt.
Yeah,
into
it's like
marine
it is
boundaries.
really, really. I mean, they
And the salt cloud physics will change the properties of the clouds. But it's, there's advantages and disadvantages to that. And there are other scientists in our, who are sort of.
I've got like 100 years
who are
so
working on
we've of the little control. I have 100 years of the waves coupled to different atmosphere and like 65 of the
Yes,
waves.
for now, we have done other simulations that we didn't talk about today.
I think it's realistic, but yeah, I mean, that's the cooling map that we get.
It's more
Like,
this is
Yes, and so there's eventually, we're hoping to get to a point where we're combining
just get
summer
almost
land
like everywhere.
like cloud interaction,
Like, look at it, like,
long wave interaction, like
It is a
Scott
tiny
talked about.
rainy,
And then also we'll
everywhere.
eventually hopefully get to a point where
It's
we're
a tiny
simulating the aerosol
Maybe
emission.
moon.
Rather
But
than
then
just
there's
sort of
shallow,
so it's
drop
like you
in
don't
the
really even
nice
have
number
ocean.
in
The wave
model
interaction
physics.
Like it's this.
But
Through the
that's-
ocean.
It is-
So like this is
Oh,
the
like,
coverage
it has one
schematic,
tiny-
in terms of the fluxes. I mean,
That is like on a
we're
continental shelf.
hacking
So it's like how well I
partition
spent.
values
Like,
like stope strip
It was
that
really difficult to
go
get
into
missions.
basically a layer.
And how well ice pack even
As
represents
far as I
such a shallow-
understand, I wasn't the one who did the layer referencing them, but I can ask you.
It has a bunch of salinity
He's the
differences
one that-
because they've got the glacier stuff.
But that's my understanding.
So we tried this.
Oh, this figure, yes. Let me think.
Yeah.
The linear stuff is not published, was what Steve did.
I can pull up a
They also have the summary.
instruments which provides.
So you have a draft manuscript already?
We potentially have a draft algorithm already. I don't know how long it will take to get published.
And we haven't even.
I don't know whether or not we can struggle.
Partly because they did it really late in the melt.
I might have to fix that.
Temperature gradient.
It would also be really nice to fix our base climate. I don't know if you noticed, but like
So there's modeling and observation.
our sea ice climate just sucks.
And then
Like
we're anticipating like
E3 V3 is no
very
longer
similar
producing
problems.
like all this sea ice and
Or
sea, like
this,
sad. So it'd be really nice to have a
There's
base climate.
I think I'm just gonna name most of everything.
Fix the negative values. So
I think it's
outside-
outside try initializing this to zero instead of
Like it's like pretty low latitude.
So do I understand right, like it would
So
just,
they do have.
when you had a need, a wave that actually is non-zero, then you'd have
Very long season.
all this history of minus 999 added average in with, you know, sudden.
Yeah. I think in a year's time.
We're around.
I've been holding that in the whole morning.
Yeah.
So it's like anybody,
But
you know, wave energy, like.
I like
stuff like that, so that they can-
I mean, that would be really
If you
interesting.
do the zero
because
route,
It's
Um,
the
It's
sort of
diluting
central
the
hemisphere
value.
thing.
The-
A lot of my other research looks at increasing the, looks at increasing the stratosphere.
Yeah, I think the issue, I don't know what the actual frequencies look like, but the peak, it's just taking whatever frequency bin is the peak power.
So there's a lot of
in,
back and forth and also.
right? And so like when you have the waves, how do you
So
pick
what happens
So more
out of
localized
your fear
information
bins
be hard
was
to do over the Antarctic.
when there is zero waves
So-
there. And so I get why they picked a defined value. And I think it's real. Because we have no waves propagating to the
But so I would be
Oh,
really
yeah.
interested to see
And
what,
it's still
and the intervention in one hemisphere does to the southern hemisphere, the southern ocean.
So then they were like, okay,
It
we're
could
thinking
I
not
did,
certain location,
but then if you had only another counter of just when you don't have non, when you have a non-zero.
Yeah, that's true.
Yeah.
And.
Yeah, that's true. Like a massive when there's waves
Okay,
versus when there's not.
They're in the melt
Yeah.
season. So then they were like, okay.
But I also think they're just
Got
using
it.
zero.
It's better than.
It's better than, it's better than.
all of these things are
negative,
also
whatever. Yeah, that's what like the frequency looks
in
like.
terms of like field testing, which
And
is-
where you get like even small weight, like.
No, it's
long,
something like interesting.
Right, like it's like 20
about
seconds.
what are
Like
sort of-
that's what I would
As
expect.
far as I'm aware, there's.
So that's
basic
good.
information
And in the marginal ice zone, like I think it's, it's just the
Just mask it
decharge.
out.
shared
Well, government
resolution
could
on the-
potentially not.
on the
But again, our
southern-
government is, when there are no wave values should just be
southern
zero.
and the south pole.
And so
So
governance,
what
even
we're
if
sort
it
of
smooths out
when you look at
like
what
small
it's
values
sort
with
of
a whole bunch of zeros, it would still just be, you need to be able to like work with. Oh boy. Anyway, but like the flows that we get, it doesn't crack everything. So I don't know.
Concentration,
Like our flow size just resolution looks okay.
For doing it, which like to their credit.
You know, think about the weather. Because you said it, this using the old flow
So what?
fractures.
Can
You just say that it fractures everything immediately?
If there's a but if there's never
Like they're constrained somewhat.
then you won't.
But then we're still getting some waves through here. But they're long. Oh, and you think the long period waves are not
We did her.
like
Not as effective.
are not as
But
effective?
it's also just a combination. So
Yeah.
you fracture everything and then you reload
Well,
everything. If
yeah.
this is what time of year?
This is January 1, a daily average.
Rewelding
There's
is
one line is wrong.
This is pretty cool. So maybe, you know, and then
Mm,
also
okay.
you can
It's,
do,
look at.
Yeah, you guys were showing that yesterday, or somebody was showing it.
Like all of them.
Yeah, someone was mentioning.
They're on tonight.
Oh, that's what it is.
No, we're looking at solutions.
So when you, how do you use those things?
We don't have a solution.
Thank you for sharing.
And a resolution.
There are also variables that both at like the ice
Yeah.
I'm always happy to
I have those
there's
variables.
something-
Actually, I'm gonna look at this too.
Anything interesting
Look at
you wanna look at? I can-
I don't know. Yeah, did you wanna look at
some weird.
the details?
Yeah. They're like, the particle doesn't exist until you have it. Right. I know. That's what I was like, I'm thinking of it, and I don't know. And like,
I have no idea what's going on.
Yeah, that's what this sounds like.
Yes, it is. It is. I think we like try to get around that by using the local forcing,
Looking forward to it.
which is a point
Cool.
weather station.
A little bit.
And then
Yeah.
I need to get it. So thank
Like,
you.
Yeah,
your
it's not
public schedule.
it exists.
Like, you
Yeah,
haven't
yeah,
published
yeah,
on
which is
your
great.
stuff
Yeah.
yet.
But you will.
Oh, yeah.
Last question, and then we can take a lead. But you said this is all, they're referencing a 2024 talk. Yeah, I'm assuming these companies really like central. It'll probably be in the document.
Yeah.
How,
I-
especially the blowing snow.
Oh.
It's from like 2000.
Yes,
for
we,
season
so
three,
we
right?
do have the
Interesting.
blending of parameterization
We
in
never submitted or we submitted.
an ice packet which model, so it's like, that is happening.
This is the details
So
on
that-
all the
there's dynamics
nightmares
in that
stuff.
sense. But there's no CDS dynamics, there's no advection, there's,
And so,
yeah, we're assuming that it doesn't.
yeah, it is like a KPP profile.
Yes.
There's an
Yeah.
enhancement factor involved
Yeah, exactly.
that we reconstruct.
Those are
a
questions that
partition
you
so
would
strip
have
that we
to
want to
get
check
in.
That's as much as I understand. But
Could.
those are the equations apparently.
Your ice pack to get some kind of.
And so US, I think this is what's coming out of the
But
wave
you would have
model.
to prescribe it back.
This is
and
the stroke
prescribe
strip
that
from
the
Watch.
back. So it's more of an external representation.
I have no idea what this
But if you need, like-
CSM is doing.
Well, I can also say size is
The equator.
that are from that paper.
Yeah.
Which ice packs.
Or we could possibly find.
Basically.
Yeah.
So if you really wanted to get it,
Probably.
what happens in the
Yeah.
case of dynamics, what happens in
Citing
the
it.
Arctic?
I hope it's.
Oh,
on
cool.
somewhere.
Yeah.
Yeah, I don't know. I guess I
That's
trust
all right.
like our oceanographers.
But I do think it's like
local knows
the process
fixing
itself.
stuff for living. There's like a lot of active research, but I'm not gonna understand that this is what he says is good for our system. Like, go with it.
Yeah, I think all these guys talk to
Then
each other anyway.
in theory,
Hopefully.
that confidence into a larger model, it's all of the.
Yeah.
Toilet for.
Yeah.
The window.
Letting that are harder to understand.
Yeah.
In both this. But, yeah.
I
you
would
would-
imagine like the greatness of this, I guess, is that you get rid of the snow layer.
Yeah.
By melting it with the sea ice.
Yes.
But if you have blowing snow, then like
Yes.
you just pump, you're just like.
Yeah. So that was like an initial thing that we had to think about quite a bit. And so the snow is a problem. So this is observations from the field only, where the lines are estimates of thickness that we got from the temperature profile data. And they also give you an estimate of snow depth. But then each of the scatter plots is observed snow depth taken in the field. The caveat with these is that the protocol for measuring snow depth in the field is extremely varied for this research team. And so sometimes it represents an extreme sampling, sometimes it represents a spatial average. It's complicated, but there's a lot more disagreement between both the two independent estimates of snow depth that we have in the models or in the
field observations. And then the model estimate of thickness is much smoother than either one. And some of that is just like you prescribe an input precipitation rate. And then whether or not it snows just based on a temperature threshold, basically. And there is blowing snow redistribution, but it's just it's like a fractional readjustment of snow based on whether ice is ridged or not, which there's very little ridged ice in these simulations.
Yeah.
So the snow is definitely a problem in terms of like, if you want to study snow with this model, maybe not. Like you can get a general sense of like the flooding is reducing the amount of snow that you expect, and its effect on the ice when you do that is pretty consistent. So like this is the thickening effect that's due just to hosing or just to flooding new ice, and then this is the increasing congelation in the model because of the flooding you apply, and those are consistent with, these things are very consistent with what they observed in the field based on how much water they pumped, which implies that this is also accurate if the total thickness is accurate. But the snow stuff is, we have just like less data on it and a worse representation of it in the model. So that's also a question. But we should run and get some food. Yes. Better potentially.
Thank you.
Yeah, of course. I'm like truly love talking about this.
Seems like a lot of fun.
Yeah. Oh my gosh.
Where's everybody? And a lot of them was like, you gave me 30 minutes, is that on purpose? And I was like, no, but apparently I did. And that
I'm gonna take a look at stuff these runs.
I do, yeah.
Oh,
That's why I love these
Everybody
meetings,
on
you know,
that, 'cause-
it's,
Yeah,
it's these different things. I think it's so exciting.
yeah.
And I love the flooding of it.
You do?
I do. It's so cool, but, you know, it's so simple when you think about it, and I keep thinking, who ever thought about something, you know, like that?
Biologist.
So
I know.
someone was telling me that they do this.
Oh, for ice roads all the time.
Yeah, well, they were saying that they were
Ice
talking to like a neighbor or something, you know, that they grew up with, and they were like, oh yeah, we used to do that to the lake to keep the ice rink around longer, right? We just, you know,
Okay.
flood our little local lake kind of thing by, you know, taking water from below and putting it on top. And it's like, that makes sense. People in Minnesota have probably been doing this forever. It's gonna extend that hockey season.
There's like, okay, this is fascinating among us scientists, but, you know, do you think there would be a political interest to keep the Arctic, you know, cold? Ice,
Probably not,
with
'cause-
ice, not? Do you think that?
Coppers.
Yeah.
Fair with the.
And I think there might be a push for that, right? Because people want to make money.
I mean, I've heard you make this argument that like the ice management stuff could be useful on a local scale to protect coastlines from things like coastal
Yes,
erosion.
yes.
That's how I wish
You
it's
frame it,
considered.
yes. Uh-huh.
Not because I want shipping to succeed, but because I think that's where you could best benefit from the expense of doing this deploy.
But that's a great
to help
way of
people.
looking at it. Yeah.
You know, and
And it's not that different than building a seawall or, you know, I mean, it's just a natural way to do that, right? So,
Makes so much sense.
Yeah, however, when we were in Cambridge Bay just last week, talking to the
Okay,
hunters.
so that's where you
and-
were. I was wondering where you
I
were.
was Cambridge Bay, bloody sea eyes.
Oh, you were
Yeah.
actually doing that.
Yeah.
Wow.
It was awesome.
I bet.
It takes like less than 24 hours to freeze. It blew my mind how fast it refreezes, which is good because what infants possibly a problem is having clouds. Just 3 times better.
Listening to Phil Rouse talking about these big clothes with the hose and you just spray sea salt.
Yeah. That was also awesome because you could see you couldn't see the evaporation because it's so clean, the air, right? So there wasn't any condensation above the flooded region until we ran by with the snowmobile and then it just went.
Oh,
I was like, oh my God, that's like a cloud seating right in front of me. Oh, that's
So you were saying that the local hunters though, were not,
They were okay with it, but they also complained. They said, I don't want this to slow us down and fishing.
Yeah, we've just established. Are you ready for your special prize?
Oh, earrings?
Oh, okay.
I don't think they're ugly.
Yeah.
is it?
Cut these on the,
Where, right? Because-
on
they're
the
not.
laser cutter,
It's
but mine is
not about.
done
fishing,
on
it's more
blue
About hunting.
on
season.
plastic and yours is on white plastic that you painted. So it's not ugly. They're just like,
Yeah, I
not
agree.
as cute.
They're also, are they smaller? They're
I think they're the exact same size.
Mm.
She
They
did
are,
the same.
they just look different.
Yeah, I think she did the same pattern that she cut twice.
Alice,
I
are
know.
you not doing Jacob?
They were more.
No, he's doing it at 10:30. Oh, I forgot. Yeah, sorry, Jacob.
I described your the earrings you were wearing yesterday to Abby, and I was like,
Right.
she's
that's
she's like,
interesting.
I can make them
And
almost
it-
like
yeah.
that. She's like,
Anyway,
can't possibly get laser cut that small. They're just too pretty and you can't do it. She's very upset.
I know.
Jacob,
Then
do you want to
there's
go
the-
ahead and
yeah.
share your screen?
Logistics, governance.
But I don't know, I mean, I think.
I think,
I agree.
yeah, that works.
I find Google Chrome unintuitive.
Yeah. Google Chrome and Google Meet are a little bit painful.
What we're seeing.
Okay. Yep,
Great.
not quite.
Yep.
Yep, there it is. Looks good.
People are wandering and I'm sorry that it's slow, but such is life. Yeah.
The important people are
Meetings
here.
just
Excited.
Jacob. Sorry.
Hi.
The good news is I made a mistake on the schedule where I accidentally gave Alana 15 extra minutes and she was like, am I really supposed to talk?
Oh,
And I was like, oh no, but look, we can be on time now.
nice.
So
Magic.
You could have just gone with it.
I could have, if that's what you wanted. So I'm gonna say, let's go ahead and get started, Jacob, and people will wander in and I'm sorry, but,
Oh.
No worries.
all right. So our next speaker is Jacob Cohen. And you're gonna talk a little bit more about prediction.
Hi, everyone. I'm Jacob. I recently started a postdoc at the Cooperative Institute for Climate, Ocean, and Ecosystem Studies at the University of Washington and NOAA PMEL. And this is some work from the end of my PhD that I'll be presenting here. So I'll be talking about a little bit of seasonal prediction and a little bit of decadal prediction for Arctic sea ice and ocean heat transport. So quick motivation, recent trends in Arctic sea ice decline really just highlight the need for accurate predictions on a range of timescales, seasonal prediction for kind of smaller scale local effects and where sea ice is going to be in coming months, and then decadal predictions for when we might see further reductions in Arctic sea ice, potential Arctic ice-free Arctic summers, and things like that. To orient us, here I'm showing sea ice concentration from observations in March on the left and September on the right, the maximum and minimum sea ice extent in the Arctic. And I'll also be talking about Panarctic sea ice and splitting it between Atlantic and Pacific regions, which I've denoted the split here with the red contours in both plots. And then I'll be showing regional ocean heat transport between the Atlantic sector and the Pacific sector. So the Pacific is just the ocean heat transport through the Bering Strait. The Atlantic ocean heat transport is the sum of the transports through the Fram Strait and the Barents Sea opening. And then for total ocean heat transport, we also include Barrow Strait and Nares Strait. But the total ocean heat transport is almost entirely dominated by the Atlantic ocean heat transport anyway. And then on the right-hand side, showing the split between Pacific sea ice extent and Atlantic sea ice extent. To assess prediction scale, I'm using the seasonal to multi-year large ensemble, which is the CESM2 hindcast prediction system. So it's initialized from a forced ocean sea ice run, and it's initialized every February, May, August, and November between 1970 and 2019, and each prediction runs for 2 years. I'm verifying that for ocean heat transport just against the forced ocean sea ice run, and then for sea ice extent against the values from FOSSI, as well as observations from NSIDC. In FOSSI, we can look at the relationship quickly between ocean heat transport and sea ice concentration in various parts of the Arctic. So on the left-hand side, this is the correlation with heat transport through the Atlantic, and we can see that Atlantic heat transport mostly affects the sea ice in the Barents Sea. And on the right-hand side, these are sea ice correlations with Pacific Ocean heat transport, which, as expected, mostly affects sea ice in the Chukchi Sea and the Pacific sector of the Arctic. So we can see these local effects of heat transport through the various pathways into the Arctic. Then our next question is, how well does SMILE predict these anomalies in ocean heat transport and sea ice on monthly timescales? So for the next few plots, I'll be showing these prediction scale as a function of lead month on the y-axis. So as we go up, we're predicting further out into the future. And on the x-axis, we have target months, so the month we are predicting. There's a lot of white spaces because we only initialize 4 times per year as opposed to in every month. But we can still get a sense of the patterns of prediction scale. So for total ocean heat transport, we see scale across all target months out to a pretty good number of lead months, at least like 9 or 10 lead months. We have significant prediction scale as noted by the dotted squares. When we split this between Atlantic Ocean heat transport and Pacific Ocean heat transport, we first note that Atlantic heat transport, as I said earlier, looks a lot like the total picture. We maybe have a little longer term heat transport prediction scale in January, for example, but generally it's similar across all target months. This is not the case in the Pacific sector, where we see that we have much longer term prediction scale in these shoulder seasons, late spring and late November or late fall in May and November, and very little prediction scale outside of these months. We do the same for sea ice extent and see that for Pan-Arctic sea ice extent on these monthly timescales, prediction scale is pretty steady across all target months. We have scale up to about 4 to 6 months across all seasons. In the Atlantic sector, a similar picture, except some longer term predictability up to about a year in January and February, which corresponds a little bit to the ocean heat transport scale as well. But this is much clearer in the Pacific sector, where again, we see these shoulder seasons that have this longer term predictability, whereas outside of these, we have much less prediction scale for sea ice extent. And some other work has showed that this is not an entirely new result. There is this relationship when the sea ice edge is really close to the Bering Strait in the Pacific, which is where this heat is being transported. The ocean and sea ice are directly interacting, which leads to this regime of co-predictability. So quick recap for the seasonal part. We see that there's this relationship between ocean heat transport prediction skill and sea ice prediction skill in the two different sectors of the Arctic. Okay, moving on to decadal prediction. I use a similar model setup. So the CESM2 decadal prediction system is essentially just an extension of the November initialized predictions from SMILE. Instead of predicting just for 2 years, the predictions go out to 10 years, and we can take annual averages from January to December to get just annual predictions for a 10-year period after each initialization, and there's one initialization per year. And we're going to look at mostly these longer term predictions without removing a linear trend or removing this long-term sea ice loss. So I showed this plot at the beginning and kind of just glossed over and said we've had this long-term sea ice reduction. But if we look closely at this plot, we can really see two regimes of sea ice in the Arctic, where until 2007, we had this long-term decline, huge reduction in sea ice in 2007, and then somewhat steady minimal sea ice during the last 2 decades. A recent paper by Mark England looked at a large ensemble of climate models and showed that this is not unheard of in these models just due to internal variability. We can get these extended periods of little sea ice loss. But that doesn't mean it's not predictable. In 2015, Steve Yeager led a paper that looked at the predictability of this slowdown in sea ice loss and showed that changes in atmospheric circulation led to changes in ocean circulation, which led to changes in sea ice. And all of this was predictable in 2015. Excuse me. So, wow, sorry. Okay. 10 years later, we have a new prediction system, and we can look at summer sea ice in addition to. Wow, sorry. In addition to just the winter sea ice that Steve looked at, we can extend to looking at the Pacific Arctic as well. And we have a new model set up to look at new predictions. So we look at these 10-year linear trends, which we calculate in both FOSSE observations and in each of the initialized predictions in CESM2 DP. And we look at both sea ice and ocean heat transport trends. So just briefly before getting into the predictions, in FOSSE, we can see there's this covariability of annual and decadal ocean heat transport and sea ice. There's this really strong relationship in the Pacific, especially, where we see this really high anti-correlation between the trends of heat transport and sea ice. So looking at how well we predict these 10-year linear trends, here I'm showing in black the FOSSE reconstructions of the 10-year linear trends in sea ice. Blue is the observations from satellites. And orange is the predictions from the decadal prediction system. And then we can also look at the ocean heat transport predictions between the DP and FOSSE. And we see that we do a pretty good job predicting both the trends in sea ice extent on the top row and the ocean heat transport in the Panarctic and in both regions. And when we look at summer alone, we see that, again, we have these high correlation skills between, or high ACC between the prediction and the observations, both from FOSSE and satellites. And we get this oscillating pattern as well in the trends of ocean heat transport. And just as a little teaser, recent predictions show or suggest that we might be re-entering a reacceleration of sea ice loss, as we're predicting these negative trends, and they're associated with this increased trend in ocean heat transport as well. I'm still evaluating the most recent decadal predictions, so we'll see if that holds up. And I'll leave some key points here and happy to answer questions.
All right. Do we have a question online in person? Okay, Mitch, you got you. Yeah.
Yeah, if I recall correctly, the Jaeger 2015 paper focused mostly on winter sea ice extent and showed decadal for winter sea ice. So it's really exciting seeing the summer scale that you're showing, and I was curious what you think the mechanism is, because I think that the winter sea ice mechanism is kind of pretty simple. You know, it's an ice edge control mechanism. Summer, you've got to somehow get that heat up to the sea ice. So yeah, curious what you think, where the skill's coming from mechanistically there.
Yeah, I think it's a little less clear. It's harder to point to. I think the NAO was the atmospheric control in that paper. Haven't looked too much at the atmosphere, but I'm curious to look at some plots, like spatial plots of CS concentration as well, to see if we can kind of get at the CS edge. But I think we're still getting this heat into the far into the Bering Sea or the Barents Sea. So I think it could still reach the CS edge in the summer.
Great. Yeah. It'd be great to see some kind of spatial plots where it's kind of popping up. Yeah, that'd be awesome.
Yeah.
Thanks for the talk. That was great.
All right, we got one more question in the room from David.
Yeah, nice talk, Jacob. I was wondering how you handle ice advection in this, because that would be simultaneously an ocean heat transport term and a direct change in your ice extent, or in your ice volume at least.
Yeah, I currently don't. Yeah, I'd be curious how that would affect it, but I'm not sure I have a great answer for that yet.
That's one more.
All right, Dave Bailey has one more.
Hopefully it's quick. I noticed that correlations in the Baffin Bay, Davis Strait, Labrador Sea region. Have you looked into that any further? I mean, are those significant or?
Where, like?
Yeah, the blue
here
areas. Yeah.
I think that's probably, so this is just looking at the heat transport through the Atlantic Arctic, which I think if I did this for the heat transport through those regions, I would see like the red in those regions. I think there's a covariability of the Atlantic heat transport with with the like Nares Strait and Barrow Strait heat transport. So I think it might be coming from that, but yeah, I'm curious about I don't know exactly why we're seeing this negative correlation.
Well, I just noted it because like Clara Desser's done lots of nice work where you see with the atmosphere and with the NAO in particular, you do see that sort of plus minus signal from either side of Greenland. And so, yeah.
Yeah. Thanks.
Well, thank you, Jacob, and thanks for being flexible with the time. Our next speaker.
Yeah, thanks for listening to my cough the whole time.
It's the worst when you just can't hear it. Hold on, I have to.
My glasses.
You can. Oh,
All right. All right, our next speaker is Alana, who's been visiting us, and I believe we'll be talking for 15 minutes, even though I accidentally had given her more.
Oh, I prepared for more, but anyway, so I'm going to talk about the role of the Antarctic bottom water in the AMOC. And this is largely the work of my PhD student, Marina, and with the collaboration of Thiago, who works at the NOC in the UK. Okay, so the goal is to understand how changes in the Antarctic bottom water impact the AMOC. It's, AMOC is a pretty hot topic. The bottom water represents 40% of the global ocean volume, and it regulates Earth climate by storing and transporting heat and carbon throughout the ocean as part of the global overturning. And you notice here I focus on the Weddell Sea because we're going to look at a lot of results from the Weddell Sea, and it produces about 50% of the bottom water as part of the global overturning. So why am I interested in this? So I started looking at OBS, and recent OBS show a decline in the bottom water transport. So on the left side, you see bottom water for about 16 north, and we see a reduction in about 12%. And on the right side, we see the volume of bottom water with a reduction about 30%, and this was entirely done on the Weddell Sea. And we see that the largest decrease are in the densest water classes, which are the curves on the bottom, the orange and the blue. So that was the motivation. So why is it reducing so much, and what is the impact of this reduction in this bottom water transport? And just a little bit of context, how are we going to analyze this? The Southern Ocean is very complex, and, I try to put it schematic, very busy schematic with everything that's going on. We're looking at the dark blue circulation, which is, the deepest and densest water. And we're going to look at a quantity called surface water mass transformation. And it's really interesting because it's a measure of the air-sea exchange of heat and fresh water on the surface water density and how that moves from one density class to another. So we're going to use data from the high-res CSM, the MESA-CLIP or MESA-CLIP, to look at these bottom water properties and the AMOC isopycnal, wind stress, and sea ice concentration. So now I'm going to present some validation results. So I don't know if people from MESA-CLIP actually looked at the South Atlantic, and I'm very happy nobody cares about it, at least we do. But look at this. Is pretty amazing. So on the, we can see WOS with the data, and that was plot with the ODV, and then on the left side you see the MESA-CLIP results, and it's pretty impressive. It's very good. But I also did TS diagrams, and on your right you have several ocean stations, and that's a plot from Tally in 2011, and you can see the different water masses, and on the right we can see the reproduction, what MESA-CLIP is giving. So we have a pretty good representation of, subantarctic front, polar front, and Weddell Sea water masses. So I was pretty confident that would help me, look at what's going on. So now, I'm interested in dense waters. So I'm going to look at potential density references to 2,000 meters, just because I'm going to bin, my density for these dense levels for the deep ocean. I'm going to bin them, and then I'm going to try to look and calculate what are the water mass transformation results. And this is my first result, which is I forgot to say, I'm just using the control run for now, and the idea is then to look at historical and the projections. So what we see on the left is the calculation. We see on the y-axis is we see the density classes, and then on the And then we see the value of the water masses, and we can see, that the fresh water, which is the green, is pretty much dominating the heat, which is the red, which is almost zero. And, I don't know if you can see, there's a dashed line, which is the total, the green is the fresh water. And then we separate the maps, the spatial maps, where we can see the net, the fresh water, and the heat contributions. And it's really cool to see that, most of this water mass transformation is happening at the Weddell Sea and a little bit on the Ross Sea on the edge. The heat is also on the Weddell more towards the north, but it's about 2 orders of magnitude lower. So, it's pretty clear that freshwater is the dominant thing. So then what I did, or Marina did, is she plotted a time series of this maximum water mass transformation for the layer below 37 sigma, which is, deep, and it characterizes the dense waters in the Southern Ocean. And we can see first, in the top panel, the anomaly, and we can see there's some sort of decadal scale variability or multi-decadal scale variability, which is shown in the global wavelet spectrum. It's about 48 years. And now what was really interesting, we tried to, what's the reason for this variability? And then we looked at the sea ice concentration anomaly and did the same spectral analysis. And, we got a peak exactly at the same scale at about 48 years. And so, this started telling us, well, maybe sea ice concentration might have a great impact on what's happening with these bottom waters, these dense waters in the Weddell Sea. So it was time to look at, correlations. So in the top panels, you have, sea ice in March, April, May, and September, October, November. So we know that the seasonal cycle is working really well. On the bottom plots, you have the spatial depiction of mean wind stress curl, and then its components, the zonal and the meridional. And on the table, we have the correlations of the anomaly time series for each of the variables. And right at the top, we can see that the correlation between the sea ice concentration and surface water mass, the maximum surface water mass transformation, is pretty high. It's about significant and 0.7. So we were really impressed with that and decided to explore a little bit more. So we started looking at composites. So we took the, plus and minus 1 sigma of that time series of the maximum water mass transformation. And we decided to look what sea ice concentration looked at, for when you had weak production of dense waters and when we had dense production, denser. And what you can see on the weaker side, look at the Weddell Sea. You got these changes in sea ice concentration and formation, which has a direct impact on the production of the high salinity shelf waters, the dense shelf waters that feed directly into the bottom water. So that was kind of really interesting. So the global density circulation, we know is driven by density difference. So we got, brine rejection during sea ice formation, which is the main source of these bottom waters. So bottom line, weakened water mass transformation is greatly associated with the sea ice concentration. And I'm focusing on Weddell. It's mostly on Weddell. That's what, Mesoclip is telling me. And now, of course, when we're talking about changes in Antarctica, you're going to look at what? You're going to look at sea level pressure, Amundsen sea low. And I did the same composites for, when you got weakened water masses and when you got the strengthened water masses. And, although for, when you look at the composites on the left side, you can't really see much, but when we plot the differences, what do we see? A deepening of the ASL, especially in the Weddell Sea and the peninsula, which is the blue, which is consistent with intensified northerly winds. So basically, you know, I'm getting to what's driving these, the fact that the water masses are changing. And here are composites for the wind components, you know, so so if we look just at the differences, which are the two plots on your right side, we can see that on the top with weaker easterlies, which mean less sea ice or less sea ice divergence. So you form less sea ice, so you have less dense water production. And if we look at the bottom plot, we see the intensified northerly winds associated with less sea ice. And it was really interesting. I read, you know, a paper recently, this guy Zhu et al. They discussed with OBS, which is a guy that did the first plot that I showed with the bottom water, decreasing, and they show exactly that there's a trend in these northerly winds, which we really associated with reduced sea ice. So, discussion and conclusion. Model shows, which is great, good agreement with WOS observations for the South Atlantic, Southern Ocean water mass properties. Bottom water formation exhibits this multi-decadal variability, which is kind of interesting, and we're going to pursue this further. Water mass transformation is strongly coupled with sea ice concentration variations in the Southern Ocean. And the wind stress patterns and sea ice concentration are the primary drivers of this bottom water transformation variability. So the key finding, and you can read, and I'll read it for you, is that, you know, in the mesoclip, we can see this changes, multi-decadal changes, and reduction in dense water production with decline in sea ice formation rate, most likely driven by northerly winds. So could this process be related to phase transitions in the IPO? People look a lot at IPO and SAM variability, you know, related to ASL. So, you know, these are the next steps. And then we'll see what historical is telling us and what can we project. So that's it.
All right. Do we have any questions? Cece?
I thought it was very interesting that your water mass transformation showed all the action right on the coast, but a lot of the sea ice composite differences were very far off the continental shelf area. So it's very non-local. Yes?
It's both, I think. It's both because depending on the winds, you might have accumulation on the eastern Weddell Sea, you know, close to the peninsula, you might have more sea ice rather than less sea ice. So it's both, I think.
Yeah, I guess also there's cause and effect, like maybe you need the brine rejection, so you should have higher growth rates.
Higher growth rate, yes.
Not.
But if you have less divergence, you know, along the coast, you're going to have, you know, more covered ice, and you know, and then you don't mix enough down, I think.
Yeah.
Cool. Yeah.
Would you say that you need MESACLIP, the resolution of MESACLIP, to capture this?
Absolutely. And I must say that we first started, I don't know if you guys remember last year, I was looking at reanalysis of the Glories V12, which is a 1/12 reanalysis, and it showed severe biases in the Weddell Sea, you know, more freshening than it should have, and the trends were stronger than the real world. So, you know, this is pure gold.
All right, last question, David.
Yeah, I should preface saying I don't do much Antarctic sea ice. So this might be a very naive question. But I imagine that if you're looking in the control runs, I presume the control runs have multi-year ice in the Weddell primarily. And I wonder how these results might apply to, or how you would anticipate these might apply to a future state where the Weddell could be dominated by seasonal ice.
The Weddell has something that I didn't touch about. It has a gyre circulation, and I think that may impact more, that might have changed. And I've looked at other experiments where depending on how this gyro-circulation weakens, it brings more warm water. Think about it's a combination, I don't know. I don't know what to expect. I just hope something good.
Yeah, I think a bit more like second year ice, maybe, right? It's like,
Yeah.
Which is, the slight difference of what we might think of as multi.
All right, well, thank you so much.
Thank you.
And we'll switch to
Calculated.
Marika, but we're gonna stay in the LC.
And feeds again, so it's always different. Somewhere else.
Yeah, I'm just thinking like the auditing we're trying to go later.
Right.
Depending on what they're started
All right.
from.
All right. Oh, my image looks terrible.
I don't.
Oh, no, what happened?
Weird. There's actual ice in that. So hang on. We will make this beautiful. Alice is going to make it beautiful.
I think I know how.
Of course.
So I'll just start by saying Alana just started her talk from the ocean perspective. And that I think speaks very well to what Alana's focus is on. I'm going to start talking about the Antarctic, but a bit more from the sea ice perspective. And I actually think there's a lot of links, so we should chat more after. But I'm going to be looking at kind of smaller timescales, so decadal changes in the variance and persistence of the Antarctic sea ice. And this is benefited from conversations with a large group of people whose names are all listed here. So I thank them for chatting with me and giving a lot of input on this study. So of course, this is motivated by what we've seen in the recent sea ice changes in the Antarctic. So what I'm showing here, and it's always a little risky to use the mouse because it also advances the slides. Anyway, so this is the monthly sea ice area anomalies over the satellite record. And you can see, the sea ice in the Antarctic varies a lot from one month to the next. But also in the last decade or decade and a half, we've seen something quite different in terms of the characteristics of the anomalies. We've had really high highs, we've had really low lows, and it just looks like there's more low frequency variability. And so we can quantify that. And so I'm doing that from a number of different metrics here. So I have a metric of persistence on the upper right. And in this, I'm doing the 10-year running 6-month autocorrelation. So others have used this as a metric of persistence. And you can see that the sea ice anomalies are much more persistent in the last couple decades. The standard deviation, again, a 10-year running standard deviation is shown on the bottom left. You can see that the ice is also just more variable, higher standard deviations. And you can also see that the ice anomalies, their regional compensation has also changed. And so the lower right is showing a metric of compensation. This is just a simple correlation between sea ice in the Weddell Sea with sea ice in the rest of the Antarctic. I flipped the sign of the correlation, so negative values are on the top. So basically higher values here would mean that there's more regional compensation of anomalies around the Antarctic. And you can see in the most recent decade or so, we've had less regional compensation. The Antarctic is kind of acting more in concert in terms of its sea ice area anomalies. So this is what we've observed. There's a lot of work going on to try and understand this. And these changes have led some researchers to claim or suggest that there might be a regime shift in the Antarctic sea ice underway. So we wanted to look at this from the context of the climate model simulations that we have. I'm not using MESACLIP here, although I've started looking at those for this question as well. And so instead I'm using the CESM2 large ensemble. And I'll just note on the lower, or the left plot, you can see sea ice area around the Antarctic. This is from one of Hansi's papers from some years ago. But the CESM2 has a really beautiful annual cycle of sea ice in the Antarctic. It also has a good regional spatial distribution of sea ice in the Antarctic. And so it's, it has a good mean state. On the right, I'm showing these metrics of persistence on the x-axis and standard deviation on the y-axis from decades of the CESM2 large ensemble. And this is just from internal variability. So I've removed the ensemble mean, although I'm looking at a period in the historical record. And so you can see that in different decades from the CESM2 large ensemble, we have very different persistence and variance of sea ice area anomalies. These things are related. Higher standard deviations basically go with higher, more persistent area anomalies. And you can see the observed max and min on there with the dashed line. So we kind of do bracket what we see in observations, although we're a little bit low in terms of the maximum persistence and variance for this period. So what I'm going to do is I'm going to take a set of high decades with high variance and persistence in sea ice area anomalies, and a set of low decades, and you can see them identified there. And for the rest of the talk, I'm just going to refer to them as high decades and low decades because it's hard to say variance and persistence over and over again. Okay, and I'm going to look at what's different in those decades. So I'm trying to understand what are the mechanisms that lead to those differences in variance and persistence of sea ice area anomalies in those decades within the CESM2 large ensemble. So the first thing that seems an obvious thing to check is whether there's some region that is dominating in that change in variance and persistence. So this map here just shows the difference in the mean sea ice state between the high and low decades. You can see on the scale there, it's from, should be 0.01 to minus 0.01 to 0.01. Sorry, there's a mislabel on my color scale there. Anyway, the differences are really small in terms of, and these are means across about 200 years, right? So very long climatologies because I've got about 20 decades going into each of these composites. So there's not many differences in the mean state. What about the variability of sea ice regionally? So now what I'm showing is across these different regions, you can see them labeled on the x-axis there, the standard deviation and anomalies in the different decades and all decades together. And for the Southern Hemisphere as a whole, you can see there are these big differences between the high and low decades. That's by design, right? That's why I picked my composite samples. But you don't see really much difference regionally. So it doesn't look like any particular region dominates in terms of the difference in variance between these high and low decades. Instead, what you see is that there's a really big difference in regional compensation in those. So again, this metric of regional compensation, correlation of Weddell Sea with the rest of the Antarctic. There's not something actually special with the Weddell Sea. If I do these correlations for the Ross Sea and the rest of the Antarctic, I see something very similar. Basically, in these decades with high variance and persistence, you have much less regional compensation of anomalies. That's consistent with what we've seen in the last 10, 15 years or so. So this would contribute to just higher standard deviation. You have less compensation of anomalies around Antarctica. The Antarctic sea ice is varying more sort of together. Okay, so that helps to explain some of the variance differences. In terms of persistence, what we see, if we look at this regional analysis, is that the Weddell Sea really jumps out. Weddell Sea has much more persistent sea ice anomalies in these decades where sea ice around the Antarctic as a whole is more persistent. So there's something special happening in the Weddell Sea. And you see it a little bit in the Indian Ocean sector as well. And actually, we see that it looks like it's just advected anomalies from the Weddell Sea. So really, it's all kind of originating in the Weddell Sea. Okay, so why? I mean, there are these differences in variance that seem to result from a difference in regional compensation. Why would we have a difference in regional compensation? There's differences in persistence, particularly in the Weddell Sea. So what are the factors? So I'm going to quickly go through those. And it's, the sea ice is sort of a slave to what's happening in the atmosphere and the ocean. And so you'd expect that those things might be different. So what I'm showing here are just correlations of sea level pressure, high decades on the left, low decades on the right, and then or in the middle, and then the difference between them on the right. And so you do definitely see that the wind and the wind-driven sea ice variability is quite different. So I should clarify, this is for April, May, June. It's the correlation of sea ice area in the Weddell Sea with sea level pressure. And so what you see is that in these high decades, the winds are just less important. the correlations are much weaker. So sea ice in the Weddell Sea is much less strongly driven by wind variations, and things like the Amundsen Sea Low lead to regional compensation of sea ice anomalies. And so that helps to explain why we have less regional compensation of sea ice anomalies. Now, interestingly, the SAM structure, the Amundsen Sea Low kind of impact on the SAM structure is also different in high and low decades. And so what I'm showing here is just the first EOF of sea level pressure, high decades on the left, low decades in the middle, and the difference between them on the right. And you can see it corresponds somewhat with what we're seeing in terms of these correlation maps. So it does look like the variability in the SAM is different in these decades, and that might be part of the reason why you have a different role for winds. So what about the role of the ocean? So now I'm going to mainly focus on the Weddell Sea. That's where we see these big differences in persistence of sea ice area anomalies. And so what I'm doing is correlating Weddell Sea ice area with surface or with ocean temperatures as a function of depth and latitude. So basically a transect across the Weddell Sea. You can see where that transect is on the lower maps in the dashed line. And what you see in these correlations is that in these high decades with high variance and persistence, you have a much stronger connection to the subsurface ocean. And so the subsurface ocean temperature anomalies appear to be much more impactful for sea ice variations. That's true on this transect. It's basically true on transects across the Weddell Sea. These lower maps are just showing for this 100 to 250 meter depth range, the maximum correlation, or sorry, the minimum correlation, the strongest negative correlation. And you can see this is, you know, kind of a pattern that occurs throughout the entire Weddell Sea. So this stronger ocean influence can help explain that more persistent sea ice anomalies. Ocean temperature anomalies are much longer lived. And so it is part of the reason why we get more persistent sea ice variations in the Weddell Sea. And I'm just to quickly note that it looks like these are in part associated with a difference in the mean ocean state. So we see that the ocean subsurface is warmer and the waters are older, which we can look at from ideal age in these high decades versus the low decades. And it looks like this is associated with sort of an upwelling or a shoaling of the circumpolar deep water. And we see wind stress curl anomalies that actually are consistent with this. So it does look like this difference in the mean ocean state is causing the surface to have kind of more ready access to anomalies in circumpolar deep water. And that's in part what's driving these sea ice persistent changes. Okay, so key takeaways. CESM2 does simulate these very sizable differences in persistence and variance of Antarctic sea ice. It does this in its internal variability. And there's been a lot of question about whether the recent changes are a consequence of anthropogenic forcing. Here we show that maybe not. In these differences between decades with high variance and persistence and low variance and persistence, we see that there's less regional compensation of sea ice area anomalies in these high decades. And this is in part associated with a reduced influence of winds. And we also have more persistent sea ice in the Weddell Sea, which is associated with stronger connection to the subsurface ocean anomalies. And then back to those observations. Does this at all relate to what we're seeing in the observations? I mean, the observational record is short. Observations under the ice are sparse. It's hard to disentangle some of this from observations alone, which is why we're looking at models. But we do see differences in SAM structure in recent years that Schroeder et al. Documented in paper look very similar to what I'm seeing in these high versus low decades. And also there's a number of studies that suggest that there's a stronger role for the subsurface ocean in some of the recent anomalies. So we think there's something real here, or some real connections there. So anyway, yeah.
All right. Christine.
Yeah, this is a great talk, Marika. I have a lot of questions. From the atmosphere side of things, because I'm an atmosphere person, have you thought about looking at this like from an initialized prediction and decadal system point of view? Because I mean, some of these relationships that you find here could potentially help improve a decadal prediction system.
So I haven't, but I do. I mean, definitely these decades with more persistence should also be more predictable,
Yes.
right? Right. And so,
Yeah.
so I think that there's a lot of interesting questions on how,
Right.
what this means in terms of how the predictability characteristics of sea ice
Yeah.
might change
Yeah.
because of, you know, the natural variability and how it's impacting sea ice. And I think that would be a really interesting thing to look at, how predictability characteristics change in the sea ice
Yeah.
associated with some of these processes.
Yeah, I think you definitely should put that on your list.
Okay.
Your ever.
You can help me.
list. Yeah, I'll help.
So these were done in the pre-industrial control?
They're not. They're done, they're done from the historical record. So I'm using anomalies from 1870 to 1959, but I'm removing the ensemble mean here. And so I'm really just looking at internal variability.
Have you thought about doing it for the modern era without removing the ensemble mean?
I've done a little bit of that so far. I've looked at those variance and persistence metrics, and I don't see a big increase in variance and persistence due to anthropogenic forcing in CESM2.
Yeah. So is it a regime shift?
So I would argue, I mean, what this suggests is that you can get these kinds of things just within the internal variability of a model, you know, and so that might suggest it's not a regime shift. I do think, you know, it's a coarse resolution model, the ocean, and as Alana mentioned, you know, there's some issues there. I've started looking at MESACLIP because I think that's an interesting tool. MESACLIP has very different things in terms of things like regional compensation of anomalies that are outside of the observed record. And so I don't know what that, there's a lot to look at with MESACLIP in terms of how it's simulating sea ice and some of these properties of sea ice. And some of that might be real, right? It might just be that we don't have that many samples from the observations, but CSM2 nicely sort of brackets the observations. MESACLIP has things that are outside it, which I'm still not. I only made plots last week on that, so still more to look at.
Yeah.
Yeah. Hi, everybody. I think my question quite naive, but I think it may be good to post here to this group. So Marika, so when the CS model in the CES, do you treat the CIS in the Arctic, Antarctic the same way?
Yeah, they use the same model with the same settings. They're exactly, I mean, they use the same model. Yes.
Right. And then what about the land fast ice?
So in these simulations, we have no explicit land fast ice. We have no land fast ice parameterization. So that is something that's missing in the CESM sea ice model.
Yeah, I was wondering because the way the ice form in Antarctic and Arctic quite different. And it's possible some of the ice in the marginal seas could be part of the land fast ice, not really the same way as the sea ice form in the Arctic.
Yeah, and so in CSM, there's a land fast ice parameterization in the sea ice model, which we don't use within the CESM simulations. And it also, it might not be appropriate at these resolutions anyway. So,
I see.
So there's some complications there, although, so Moyan, we don't use there's no land fast ice kind of simulated in the model. Yep.
Thank you.
Yep.
All right, we're gonna do a last one from Mitch.
This should be pretty quick. Just regarding the regional compensation point, do you think the ocean's also playing a role there? In other words, are the subsurface ocean anomalies in the Weddell Sea zonally coherent and kind of driving a circumpolar coherent anomaly, do you think?
I don't think so. I've looked at the kind of similar transect in the Ross Sea to see if I was seeing anything different there. And it doesn't, I don't really see something outside of the Weddell Sea in terms of things like the influence of subsurface ocean anomalies on the sea ice. So I do think that there could be some relationships between the lack of wind driven or the spatial patterns in things like the SAM and the changes in like wind stress curl in the Weddell Sea that are kind of contributing to this shoaling of the circumpolar deep water. So I think there could be some things that are linking these that are why they coincide. They happen in the same decades. But I haven't dug in enough to say that conclusively. So,
Okay.
but there are, I can show my wind stress curl. There are differences in wind stress curl in these high versus low decades that are significant and look to be part of the reason why you get the shoaling of the circumpolar deep water. And they may have some correspondence or some relationship to those kind of other sea level pressure changes.
Great, thanks a lot.
Yeah.
All right. Thank you, Marika.
Yeah.
Because of time and that I should have caught things, I am not actually going to speak, and we're going to go straight to Courtney. If you're interested in Antarctic biophysical connection stuff, there was a CGD seminar last week that Marika and Kristen and Laura did, and then I'm giving a seminar in March. So I'm sorry.
Sorry, I took it.
No, you didn't.
No.
I hear Alana did.
I put
Yes,
super
the
fast.
All right. So I'd like to start off obviously by thanking my collaborators on this project. So when I think of the polar oceans, I typically think of a system that's very controlled by light availability. Obviously, due to the polar night in the winter months, meaning there's no light available, and then even into the spring, sea ice and snow blocks light in the surface ocean. So when we typically think about phytoplankton blooms in the polar ocean, we've historically thought of something like this, where phytoplankton are only growing around the breakup and retreat of sea ice. There was a cruise in 2011 that disrupted this idea. They went out in the kind of pre-bloom environment, anticipating seeing something like this under the sea ice, where we have sea ice at the top and then a nice blue ocean with basically no phytoplankton beneath it. And instead, they observed something that looked more like this. Still ice at the top, a meter of fully consolidated ice, but beneath it, one of the largest phytoplankton blooms ever observed in the world's oceans. And since this first observation of an under ice phytoplankton bloom, blooms like it have been reported all throughout, sorry for the weird Canada and Alaska and Russia and Scandinavia, my goodness. Since this first observation in the kind of Chukchi Sea region, blooms like it have been observed throughout the world's oceans, the Arctic Ocean.
I'm seeing if I can get the right thing, but
I think I'll be fine. Don't worry about it.
Okay.
This really nice work by Chris Horvat using floats has kind of found that maybe these blooms are relatively well distributed throughout the Southern Ocean as well. So there have been really, all these were cruise-based in situ observations, but the only evidence of under ice blooms in the Southern Ocean has been floats, which have been out in a variety of sea ice concentrations and have observed increases in biomass prior to the full breakup and retreat. So I think these kind of lines of analysis have led us to maybe alter our sense of when blooms are happening in polar oceans, possibly due to thinning sea ice or the proliferation of melt ponds. There's increasingly evidence that blooms can happen under fully ice-covered conditions, and that in some cases, the kind of surface ocean can be entirely drawn down of nutrients with no phytoplankton blooms in the summer months where we historically expected to see these blooms. Not surprisingly, this can have some pretty big consequences potentially for ecosystems. So when we typically think about a summer-based phytoplankton bloom, that will the warm waters, relatively speaking, allow zooplankton grazing on that biomass, which then leads to a lot of food available to upper trophic level organisms. But instead, if these blooms are happening under really cold conditions, zooplankton growth is not able to kind of keep up with and consume much of the biomass generated under ice, which could lead to less food available for our upper trophic level organisms. And it also could mean that the share of carbon that is exported could increase. So we might see an increase in carbon sequestration and also in food available to benthic communities like this clam and this amphipod, and even to things that graze on benthic organisms like this walrus. So I was curious to understand a bunch of things about under ice phytoplankton communities. These are typically only observed or studied using ship and occasionally float-based measurements. We have no ability to study them with satellites, essentially, because they're invisible under the sea ice cover. So I really wanted to understand how much NPP is generated under sea ice in the Arctic and Southern Oceans, how this under ice NPP might be changing over time in terms of its amount, its spatial distribution, and then under the sea ice conditions that, including concentration and thickness, that under ice blooms are forming in each of these regions. And for this, I relied on a special run of the Community Earth System model, version 2 specifically, and a less melt parameterized run. This version had 4 phytoplankton, 2 zooplankton functional types, and also daily output of light at the ocean surface and fractional coverage by each sea ice thickness category, as well as a bunch of other daily variables. And that allowed me to calculate hourly light limitation terms under each sea ice thickness category in open water, which let me partition daily NPP based on those light limitation terms into the area of sea ice thickness category within each grid cell. So I'll first show you the proportion of NPP generated under sea ice in the 2020s in the Arctic and Southern Oceans. When I first look at this, the Arctic obviously jumps out. There are places in the Central Arctic where almost 80% of total production is happening under sea ice within each grid cell. The Southern Ocean looks pretty underwhelming at first glance, but kind of surprisingly, there's about the same amount of productivity generated in these two regions, about 100 teragrams of carbon per year in each location. So a pretty substantial amount, nearly 20% in the Arctic and still like 14 or 15% in the Southern Ocean. Under ice, I was also curious to understand how under ice NPP is changing over time. So in the Arctic, since the 1920s, we see in this model run an increase in productivity until about the 2030s. And following the 2030s, there's a really substantial decline in productivity. In the Southern Ocean, there's really no change until about the 2050s, 2060s, when there's a more modest decline in productivity. And both of these can be tied really closely to changes in sea ice conditions in the two regions. So overall, yeah, we see that there's a decline in productivity under ice in both hemispheres. So I also want to understand the kind of conditions where these blooms would happen. CESM partitions the ice pack into 5 different ice thickness categories. And in the Arctic, we see that under ice productivity is largely generated under, there's about 45% generated in the thinnest sea ice thickness category, but then the next 2 thicker categories also can produce pretty substantial amounts of under ice production. In the Southern Ocean, however, 75% of total production is generated under that thinnest sea ice thickness category. And this is probably not surprising to all you sea ice people who understand well that the differences in snow are really substantial between these two places. So we'd expect a lot less light being transmitted through relatively thicker sea ice in the Southern Ocean. I also looked at the differences in kind of where in the ice pack these productivity was generated. So dividing up based on daily sea ice concentrations, the ice pack into the consolidated ice zone with greater than 85% sea ice concentration, the marginal ice zone with 15 to 85%, and then the open water zone. And in the Arctic, we can see that about half of total under ice production is happening in the consolidated ice zone. So that matches pretty well with that first image I showed you of a bloom that we've observed in the Arctic. In the Southern Ocean, however, more than 80% of production is happening within the marginal ice zone. So it's quite a different environment than we're seeing in the Arctic. You really can't get these blooms generated under the fully consolidated ice that you see in the Arctic. And that fits really well with Chris Horvath's observations as well. So the final thing I was interested in looking at was how under ice NPP is changing in its spatial distribution over time. And in the Arctic, we can see that in the 1920s, productivity is largely on the shelves. You can see the kind of 1,000-meter depth in blue here. And by the 2030s, that productivity shifted into the Central Arctic just due to the thinning of the sea ice, overlying sea ice pack. And then by the 2090s, of course, we see that there's a really substantial decline in Arctic productivity. So we see overall this kind of poleward shift over time, but then eventually a very substantial decline in Arctic production. For the Southern Ocean, productivity is initially kind of relatively well distributed across the Arctic. Maybe there's a bit of a hot spot around Ross Sea, but by the end of the century, we see that there's a ton of production happening within the coastal zone. So that the continental shelves see a huge increase in under ice production over this time, as there's kind of a decline out further in the ice pack. So again, we see a poleward shift in these blooms due to these changing ice conditions. And in this case, that moves productivity onto continental shelves. So overall, this work shows us that there's about 200 teragrams of carbon per year of net permanent production generated under sea ice, and that's split relatively equally between the Arctic and Southern Oceans. We also find that NPP's likely to shift poleward and decline in magnitude over time in both hemispheres. And then the conditions that support blooms in these two places are really different. That in the Arctic, we get blooms under consolidated thick sea ice, and in the Southern Ocean, it's largely under the thinner ice that's in the marginal ice zone. And I think that this has some pretty important impacts for the kind of balance of food in the pelagic versus benthic communities. As we're shifting these blooms out from the continental shelves and into the deep ocean in the Arctic, or from the deep ocean onto the continental shelves in the Antarctic, that will likely have some pretty big consequences for the kinds of ecosystems that are supported. Thank you so much, and I welcome any questions.
Questions? Alec?
Yeah, I may be surprised by that point about how much you're getting under consolidated thick sea ice. Is maybe the point that it's consolidated and thick, but not very ridged, and so you're not getting much of the very thick ice. You're getting a lot of like middle ice thickness.
Yeah, so I should say that the thick that I'm referring to for the Arctic is, sorry for that. This is 0.6 to 1.4 meters thick, the thin ice, and then this is 1.4 to 2.4 meters thick. So it's still not particularly thick. It's just obviously a lot thicker than the ice distribution we see for the under ice blooms in the Southern Ocean.
Right.
Other questions, Molly?
No, yeah, sorry, I was halfway through deciding whether or not it's a good question. But I'm curious how much of the conclusions about differences in where the blooms form in terms of ice type for the Arctic and the Antarctic is just about the like base state thickness conditions in those places.
I think it's very much tied to the conditions in those places. I think we don't see a ton of productivity, for example, in the Central Arctic in the 1920s because the base ice is just too thick. And then only as you thin that ice sufficiently are you able to grow an under ice bloom in that sort of region.
Okay, but then the like number of blooms that are occurring under thinner ice in the Antarctic, is that simply just because more of the environment is thinner ice in the Antarctic?
That's a part of it. And I'm sorry I don't have these slides right now, but I have in the submitted paper version of this, I have a nice plot overlying the sea ice thickness categories of the actual distributions of those categories over time. There's certainly more thin ice in the Southern Ocean, and the thicker ice in the Arctic is a slightly better habitat for under ice blooms, if that makes sense. Even accounting for the difference in thickness distribution.
Got it. Okay.
David.
Is part of the story about the snow cover on the ice here too?
That's a really good question. I imagine that is something I did not investigate at all, and I imagine it's an important component. But productivity is generally peaking in like mid to late summer, so and that is true of these blooms as well. So I think that the snow is probably too much of an impediment to a real much phytoplankton growth until it's like melted.
Right, and I guess that was what I was thinking of, is in the 1920s, you might have had snow persisting later through the summer. And, and maybe in the Antarctic, I don't know. I mean, the snow generally lasts all year round there. So I kind of wondered if there was any role in that too.
Yeah, that seems like something I should have investigated. Definitely.
David.
Yeah, the snow, even like is still mostly melted by July. So I don't know about like late summer. But what I was gonna ask is, hypothetically, if a new version of the model were to show considerably more light transmission into the upper ocean, even in pre-industrial control conditions, do you think these results might change much, or how do you think the results will change?
I am anticipate that we have more production happening. We have a greater proportion of annual production happening under ice. And maybe like a fun additional note I would make for you is that in the 1920s, so I haven't showed it here, but I've also characterized how much productivity is happening in the open water portion of the grid cells that are, for example, 85% sea ice covered. So the kind of lead contribution, and the lead contribution is really important early in the 1920s, but it becomes way less important by the 2030s. By the 2030s, the leads are barely more productive than the overlying sea ice, than the part of the grid cell that's covered by sea ice. So I think that would probably maybe enhance that effect even. So.
All right, I think we had one last question from Molly. I hope it's fun. How do these phytoplankton blooms respond to brine rejection, basically, or freshwater input from melt? Do you have any idea?
So I guess the phytoplankton want a relatively shallow and stable water column where they will have ample light to grow. If we take the 1920s example, perhaps, I guess in the 1920s, I anticipate that brine rejection would lead to a deepening of the water column, which might cease the under ice bloom. But by the 2090s, one of the main limits on their growth is not light so much anymore, but rather nutrients. And so the increase in nutrient availability that would be made by an increase in mixing might support more under ice production. So I think that there'd be a changing effect over time, would be my guess.
Yes, you could try and find like the optimal conditions.
Yeah.
Based on this kind of training data, like what do you actually want? If you wanted to maximize NPP production, that's probably like a sweet spot.
Yeah, and I think that maybe speaks to what is the point of under ice NPP? Do we want it to support pelagic ecosystems? Do we want it to lead to like a ton of carbon being exported to depth? Different people might have different answers for that. And so yeah, always a fun thing with VGC, like what the selecting the optimal is, maybe having some big consequence, unintended consequence on something else, some other part of the system.
Cool. All right, thank you, Courtney. All very good today and yesterday. So without further ado, I think the last thing we had, oops, I just closed the thing I wanted, was I want to have a discussion, kind of a continuation from yesterday. And I'll see if I can change, I'm trying to make sure I can see the comments, adjust the, sorry, people online, hold on. Okay, we have chat. If you turn on your camera, I think we will see you. And I'm just going to leave this up as like a discussion topic. But I also have an agenda, which is that I wanted to get more feedback from people here while we're all here. So these are the things, I think I posted some of them. Some of them are from yesterday. So one of the things I wanted to at least bring up, we don't have to settle everything today, is people who are interested in writing a paper about CSM3 when it comes out. We don't have like a special journal set up yet and stuff, but you know, I have been operating under the assumption, for example, that like David Clemensoul is going to do a melt pond study and write a paper about CSM3 melt ponds, and CC is probably going to do something with waves and maybe like how waves are changing over time. things like that. But I don't know if other people have had thoughts that they want, you know, I'd really love to look at this or whatever. And mainly I just wanted to get an idea of who is interested so that when we do have info about a special issue, I can share that with you. And also to make sure it's not like Alec wants to do melt ponds and David wants to do melt ponds, and then they're fighting each other on the paper, and maybe they can just coordinate.
I'm gonna win.
I know we are supposed to just fight now these days. That's but so that was one of the things that I wanted to bring up. I brought this up yesterday, and this is sort of just presenting it, but let us know. So if you want to run experiments with the Polar Climate Working Group allocation, that should still be easy. And if you have done this in the past, I'm going to be bugging you soon for a figure or two because I have to write the report about how we used it. They're trying to minimize the amount of work for us so that we don't have to write a full proposal about how will we use Polar Climate Working Group resources for the next 2 years, because it often changes dramatically over 2 years anyway. So if you want resources, you should email me and Ed and Dave, just so we're all aware of what's going on and we're not promising hours to people and then not the other people don't know. If it's a smaller allocation, less than 1 million hours, we almost certainly can just say yes and support it. If it's more than that, we just have to check and make sure that, you know, it's not going to be problematic. I also wanted to point out that there is a process for getting university large allocation requests. So if you wanted to do a bigger experiment that's like 20 million core hours, you might want to go through that channel because we won't be able to do that. Or you're like, I want to run Mesa Clip on my own, whatever it is. But that we also, for things that the Polar Climate Working Group, like if we want to have some large-ish ensembles, whatever we're going to call it with CESM3, it might be that Dave Lawrence asks like all the working groups to contribute 5 million hours or something like that. So just a better understanding about what people would find really valuable to have as community data sets available. And then I just had miscellaneous other topics that had come up, like machine learning enabled CESM. If you're interested in that, the high resolution Mesa Clip, regional stuff, anything else that's not on there. So that's what I put together here. I'm happy to just kind of open it up. Dave has a comment, and we'll try to keep track online and everything too.
I think it's worth mentioning with the allocations too. So our current allocation ends April 30th, and we still have 3.5 million hours left. So even if you didn't put in, you know, previous requests for allocation, you know, let us know, and you know, we can definitely, you know, give you some of this. So yeah, yeah. I mean, we need to use it before the end of April. So yeah, still something to think about.
So I'd say if you want to do that after this meeting, email me and Ed and Dave. And I put a smiley face there about getting in touch because we are friendly people. I respond immediately. Yeah, but just email us so we know, so that it's not like, oh, we just promised DC 2 million hours and Alec 1 million hours, and now we can't do whatever development run we need to do.
Right.
So
we have a separate pot for development. So that's
just roughly what it, like 100 years of CSM3.
Yeah, CSM3 is pretty expensive now. I think we're talking about like 10,000 core hours per year. Yeah, it's bad. So multiply by 100. So
one of the reasons we don't have that is we've been doing most of the development, pretty much all the development with the low top model, and we're planning to release the mid top. Like the mid top model will be used for the deck experiments, but I don't think we have it because that's not what we've mostly been running.
So even this like 287 run, that's with low top.
Yeah, that's low top.
We were aware as what happened with CESM too, like there could be unintended consequences of the shift to mid top, but we just feel like it's just taken them a while to get it together. So we don't know what that is yet.
Right. And the other thing I was going to highlight too, I don't know if it's come up so much, but we have this strategy too, where we are going to use the full chemistry in the mid-top model, and then we'll save the fields from that, like the aerosols and so forth, so that we use that as boundary conditions in the standard experiments. And so it's kind of similar to what we do with CSM2, where we had CAM6 versus Wacom. It's kind of going to be a similar thing. So,
Oh, and I should say all the development runs also have not yet had BGC on, and so they're working on the BGC spin up and like that.
Collecting most of the system up here.
exactly. Yeah.
I think they were hoping there'd be like a better method for it rather than brute force, but I don't know that
Right. Yeah.
came
the
to
spin up
fruition.
Spin up is a challenge. Yeah.
And they have run into some, like, Gustavo and Ian talked a little bit about the Antarctic bottom water formation. I think that kind of came up only in the past couple weeks when BGC started. Really, it was like, okay, this is close enough. We can start a spin up, and they're like,
Right.
oh, this looks not good. So
Yeah. And we have not started. Our CMIP experiments at this point are supposed to be emission driven, but we've been doing everything concentration driven to this point too. So that'll be another change.
Even the historical will be emissions driven?
Yeah.
Wow.
Yeah.
That's great.
Yeah.
And we're supposed to release a model by June.
Exactly. Yeah.
Yeah, which brings up, can we still modify anything in the CIs?
what are you thinking?
Hashtag we throw that in.
I mean, we could implement Aeron's new emulator for the ray fracture and speed up the code. No, don't go there.
Yeah, I think at this point it's too late. It's too late for sort of science changes. We're at the point of now bug fixes and tuning. But one of the other topics is just other experiments that we would think about. And so we would want to do a whole bunch of other sensitivity runs with maybe this, Dia Zhang's machine learning algorithm. I wanted to talk to you more maybe about wave model resolution experiments and things like that. And so, yeah.
Well, the only other two things I would think of are maybe model tuning. It's kind of rare. Anyone's you, but the welding kernel, and it won't, like, no one else will notice, but look closely. The other thing is possibly this point I was making in the joint session yesterday, that there kind of is a bug in the wave watch mining. There's lots of bugs.
Let's not limit the number of bugs on WaveWatch.
But the nonlinear source term is multiplied by the CI's concentration, so that's dumb. It shouldn't be. I mean, I guess I could do a sensitivity experiment quickly if that's.
So my sense is something like that one might help with like a bug, whatever, or a bad thing we're seeing with ACC might be something that we can justify. So like any change, we have to go to the SSC and tell them why we want this change now.
Okay.
Right.
I mean, I think parameter tuning, maybe not, but something like this, we could be like, well, we thought this was a bug. We could test, like Dave could start a test and we could see if that helps with it. And if that's the case, we might be able to change it. Something like the emulators, I think they'll be like, no, that's too much at this point. But for the machine learning enabled CESM, I think testing your emulator for that and Dia Zhang's, those sorts of things would be great. And it's actually kind of good in a way if it's expensive and then we have an emulator and it's not so expensive and we'll be like, look how great machine learning was. Keep giving us money, people. We're useful. I mean, I think being able to show that machine learning can help with performance would be beneficial as well to the project. So I would say we definitely should do some tests with your emulator. It probably won't get into that, almost certainly.
So the one thing I was going to say is that the reason they had a look of fear is because the emulator is trained on the extended bounds. So you'd have to completely, hence the look of fear.
Yeah.
You'd have to completely and retreat. But that would be a question if you'd want an emulator like that, and I guess how far you'd want to go with it. Because there's obviously other improvements that you can make. Because at the moment when they do wave fracture, they take the mean of the thickness categories, and this is what we're talking about. And I think Laddie's alluded to is you could make an emulator for each thickness category, see how it fractures independently, which would be like many networks. It'd be like 30 network or more.
I think we should continue to investigate that. And like I said, I think something like that could end up being in CESM and LE or whatever it's called. But for this like June.
Oh, yeah, no.
I don't think those
Yeah.
changes will happen.
It's really good.
Yeah.
And with the welding kernel, if you think it might like dramatically change the ACC, maybe we can make that case. Otherwise, probably not. It could go into like CESM 3.1 and we can, you know, with Polar Climate Working Group resources, we can test it, but
It's not that urgent.
okay.
I think it is worth thinking of these things in the context of, you know, what are the developments post CES?
Yeah, yeah,
And
yeah,
having
yeah.
a list and thinking about sensitivity tests we want and all of that.
Yeah.
So, you know, model development doesn't end with this model, so, right?
Okay, thanks.
I also think it'd be useful to think as a group about kind of coordinated experiments. I mean, there's resources for individuals to run experiments, but it seems like there's some things that are being very highly utilized, like the nudged wind runs.
Right.
I think there's a lot of interest in those from a lot of different science, you know, questions and science topics. So should the Polar Climate Working Group, as a group, do a nudged wind run that we all help design, so it's kind of meeting all of our needs, and then is available to everybody? I think that we probably could come up with a set of simulations like that. I mean, I think wave ice stuff is another obvious candidate, right? Some simulations where we turn off the wave ice stuff so people can look at impacts in the southern regions, in the Arctic, et cetera, et cetera. But I think we could dream up a set of kind of standard Polar Climate Working Group runs. We help design together, we all have access to. We can all do cool science with them. And those would probably be the two on my list, the turning waves off in the sea ice or without the FSD basically, and then a nudged wind run. And I don't have specifics about exactly how those are designed. So I think we could talk as a group, like, are the nudged wind runs an Arctic one and an Antarctic one, or a bipolar one, or global one, you know, whatever. I mean, and we probably would want input from people like Ash and Jen and Ed.
I feel like for those in particular, it would be really nice if there's like a broad interest in just being able to turn on wind nudging for an experiment that you want to run. It would be really neat if there was like a documentation page and like a code configuration that you could just import that would allow you to do that, rather than having to kind of like hand the process around from person to person.
We have talked in
As Claire said, there is.
Oh.
Yeah.
Oh my gosh, amazing.
Yeah.
Never mind. And we have talked about trying to gather nudged experiments that have been done with CESM 1 or CESM 2. And so these could be with CESM 3. And I do think it's valuable. We haven't gotten around to doing that.
Thanks, Claire, for that
previous
link.
versions. And I was going to type up notes from this and the other discussion so that you guys can see a summary of what we talked about, or maybe I'll put it into ChatGPT, whatever. So yeah, I think nudging is something that people have expressed interest in the Polar Climate Working Group for a while. Wave ice experiments, I feel like we all have interest in some combination of those, maybe with different fracture schemes or just on versus off. As we heard yesterday, we'll have to work with the ocean group if we're turning it off entirely, because now all of their like mixing schemes on this.
Yeah.
So it might just be it's not coupled to the ice or whatever.
Yeah, we could turn off the wave fracture and the FSD, and it would still attenuate waves just fine.
Yeah.
Yeah. And
The ice model wouldn't know one way or the other one.
we did do that.
Yeah.
You know, in a few experiments. There was a while where that was a proposal on the table where it was only going to be a one-way coupling. But
It'll work.
we struggled with the Lab C and those configurations, right?
I think when we get to that, we'll have to see if that continues happening, and if, you know, maybe we can branch from later in the control run when it's not as, there are ways that we can hopefully get around that.
I also think that would be a really useful science paper to write, that, you know, having wave ice interaction leads to a reduction in Labrador sea ice and fixes this problem. I mean, that, to me, that's actually, we've talked about that. We think that's what's going on. I think experiments to actually document that are carefully done, not in the kind of development phase of CES3, and write that up would be actually a nice.
It seems to be robust, because that's a signal that I see when I do the isolation of wave ice experiment.
Yeah.
Reduction of ice in Lab C. So, yeah.
Yeah, so we could look across models too if it.
That'd be great.
Yeah.
So I don't think we need to tune it out or something.
Yeah.
That's one of the results.
Yeah.
I think sort of jumping off that idea, but not about wave ice, is that for some of these tuning runs, you could think of them as sensitivity experiments, and it would be useful to like, for example, the R snow parameter, like have a couple of runs, like, right, I presume we're going to need to do those tuning runs anyways, having them archived and in a version of CESM3 that it would be reasonable to look at, as opposed to it being something in its development cycle. Just because I think stuff like the paper Jen K led has been very useful in the observational community, in informing us like, where do we need to target albedo measurements? What kinds of accuracies do we need to target albedo measurements? But like otherwise it's sort of in the kind of gray literature of like, oh yeah, like, in CESM2, don't look at the pond albedo tuning versus like, right? So.
Is there anyone else? I mentioned a few possible CESM3 manuscripts. Is there anyone else who is thinking, I'm interested in X and I'd like to look at that? I think there will be like a documentation. Hang on, Ethan. Like maybe I will lead a documentation just of like general polar climate, and I will probably ask people for some help, but like that will not be a full dive into ponds or waves or something like that. And there will be a general like CESM3 overview that I assume Dave Lawrence will lead. And again, there'll be maybe a couple figures that include sea ice, but mostly that's just like this whole model is new and different. Oh, sorry. Ethan?
Yeah, sure. Thank you. Ethan Campbell. I apologize. I missed Alice's overview of CSM3 yesterday, but I'm a little curious about the snow redistribution scheme. Point snow addition. I'm looking at this separately for the Antarctic in some work following from my PhD work. Just curious if there have been sensitivity runs done already, or it seemed a little intriguing that I think Alice mentioned I saw on your slide that snow depth is a little low in the Antarctic in this region.
No, and David had suggested this yesterday. We have not done those sensitivity experiments. So this is the snow redistribution coded up essentially by Nicole Jeffrey at Lanel, and based on Olivier Lecomte's thesis work. I think there's this mysterious 0.3 factor in there, as there is in a lot of things.
That's the other scheme.
Oh, but I thought the 0.3 was still used for like some min-max sort of thing. Anyway, it's your point is well taken that we should probably do some more investigation of this.
And I think in that context, like a snow mass budget study, which looks at the snow redistribution, some of which is in the leads, would be like, that would be nice. That's a difference in the model. We do seem to have different snow behavior. So like if someone wanted to lead a snow paper for CESM3 that maybe has a couple sensitivity runs to look at too, that could be kind of a cool study, I would think.
Yeah, I think Melinda's pretty interested in this too, and we'll have to chat more discussions with David about this too.
And I was going to say along those lines, as I mentioned yesterday, that in the advanced snow physics, we only have the snow redistribution on, but if you wanted to do a snow mass budget study, in addition to testing that part, you might test other parts too and be able to provide other insight about, I think we were getting some funky results, and that's why we don't have all of it on, but better understanding that and how it behaves in CESM3 would be valuable for us as well. And I think it wasn't just the Antarctic sea ice. I also mentioned that it looked to me, from my not super expert snow eye, that the Arctic sea ice distributions, like the snow depth distributions, looked funky to me, and I'm not sure why that is too. So yeah, just, I think definitely. So Ethan, if you want to, email us and we can try to coordinate among people who are interested in that too and help you get hours to do tests.
Totally. Thanks.
Yeah, I was going to add, yeah, from our group's perspective, we're still interested in doing some of these kind of modern era comparisons, and we've had some, well, I think we got a bit confused with some of our analysis we tried to do with some of those development runs a few months ago. But yeah, it's hard because it's, we're at that intersection between the historical and the forced simulation. So I'm not sure how much we can do prior to the kind of scenario runs. But we've got things set up at least so that, as runs come in, we can see how they look and yeah, do the kind of freeboard thickness style assessments.
Does anybody have a strong opinion about, I'm trying to look up, I looked up what the new forcing names were. For a scenario, when we decide this, does anyone have strong opinions about they were called HMMLL, VLHO, VLLO. It's like high, medium, low. Does anyone have any, is anyone?
Is that like the code names for the?
Yeah, just, there was like SSP 370 and RCP 85. Now they're just going with single letters, apparently. It's just high, I don't know. As Dave Lawrence said, they haven't actually released all these yet, so we can't even do those tests yet. But, would people, I think there's some political push against doing like super high scenarios now, this executive order to not look at RCP 8.5 ever again, whatever that is. But would people feel like a moderate scenario is reasonable? It looks, I can't share this as easily, but the moderate scenario still kind of goes up. It looks like moderate, low. There must be some sort of mitigation because
I think it's useful to have a scenario that is sort of comparable to the CESM2 large ensemble, which is the three.
Yeah.
I mean, just it'd be nice, we have the CESM1 and CESM2 use quite different forcing, which complicates comparisons across them. We might as well try to, I know they won't be exactly the same, but
okay.
That's would be my argument, which isn't the highest scenario. So hopefully that'll be okay.
If they haven't sent these to you yet, is there a place where the assumptions about non-scientific contributions to the scenarios are laid out? Do you know?
What do you mean?
Like the assumptions about what kind of mitigation might be happening in addition to emissions, that kind of stuff.
I mean, there's a whole group for CMIP that's putting these together. I don't know if they're still accepting comments for how mitigation aspects would be done, if that's
more. I'm is this iteration for SAM7, is the explanation for those scenarios available anywhere?
Maybe online, but maybe not if they haven't released them officially.
Yeah, Claire just put something in
I just put the preprint to the scenario paper.
Okay.
Cool.
Thanks, Claire.
Yeah, we were surprised just at the differences just in the short term from the different scenarios. I don't know, maybe I'm naively thinking 5-10 years it wasn't as big of a deal, but it still changed instantly.
When are the scenarios initialized for CMIP7?
2021, I think.
Yeah, I think that's what we heard yesterday. Yeah.
So they do have IDs that are much less intuitive than HMMLL. But anyway,
Yeah.
I can send this out when I send out notes for people who are interested. And the figure I showed yesterday of the different scenarios was from that paper. So, but I will be honest that I haven't delved into the scenarios, partly because I think Isla and Dave Lawrence has done the most with it. But because of weird political stuff, I've been I have enough other things to do.
Okay.
Anyone else online? I know there are some of you and you have piped up some. I want to make sure you can speak up if you want. All right, any other so we talked some about papers and the resources. Anything else that people want to talk about?
Just a quick question about the resources. Sorry, how competitive is this generally? So there's some issues at NASA right now about some of the big NASA HPCs that maybe being kind of decommissioned, and that's all becoming a huge mess, and a little bit unclear where we're supposed to do kind of big runs and things. But we have CSM on the NASA servers, but it's unclear how long we're going to be able to keep doing that. So there's a chance that we might want to switch over, but I don't want to make your life.
I mean, there's not like a hard and fast rule. That's why I was kind of like, okay, if you want a smaller request, we can probably support that. If a single user ends up taking up, like 50% of the resources, that's kind of antithetical to what it's supposed to be for. In the past, it's always been like when people email us and we kind of try to make sure there's enough, and we had to write a full proposal for that. And then what would always happen is some people say, oh, I want 1 million hours to do blah, blah, blah. And then they never do it. And we email them and we're like, hey, are you going to use this? And they never email back. And then we're like, well, we have 6 months left and we don't know what's going to happen. So who wants some resources? And then occasionally I think they come back and they're like, oh, I want to run. And we're like, too late. So in this sense, like,
Apologies if that was me, but
people can ask, people can ask throughout the cycle, and like, it probably won't be as competitive at the start. And as we get close to the end, if you're like, oh, we want to do a lot, it might be that we've drawn down.
Are you asking specifically about like the university allocations in terms of that competitiveness?
Yeah.
I don't really have a good sense of that. So those are reviewed through a separate process, and I've collaborated with some university groups who've gone that route, and I've generally found pretty good success rates with the groups I've been involved with. But yeah, I don't know.
10 of them. So
Yeah.
I've
Right.
never been cut.
Right.
Reduced what I asked for, but we asked for something reasonable.
Mm.
However, you have to have an NSF.
Yeah. It has to be related to an NSF.
But your students can ask, but you don't have an NSF grant. But then they're limited to a small allocation of $1 million.
I remember this now. Yeah.
Yeah.
Two pots that, because we.
Yeah.
Under CESM has an allocation. And so that allocation is fairly easy for you to tap in through the Polar Climate Working Group in the mechanism, but then the large allocation request.
So, I mean, I can send this link and stuff, but for exploratory allocations, a graduate student, postdoc, or new faculty member can request a one-time allocation of up to 500,000 Derecho core hours or 1,500 Derecho GPU hours. And they say they usually support dissertations, help foster early career research, or provide some seed resources for pursuing funded research. I think when people, when a grad student asks for that, it's almost always allowed.
And they let you ask for a doubling at some point too.
Yeah. You can request a one-time supplement up to twice the original.
Even a tripling.
But that's one way the graduate needs an NSF grant.
No, the graduate
They
student.
won't double it, but they let me keep using it after the period for which the extension was granted, so they're pretty flexible.
It's a really awesome resource.
Yeah.
Well managed.
Any other topics? I will mention with high resolution, so Mesa Clip uses CESM 1, and we kind of just skipped having a high resolution with CESM 2. I believe the goal is to have a high resolution option that has CESM 3, but we haven't started trying to tune and deal with things that would entail yet.
Random and maybe a bigger question.
Anything else?
But anything else? What does the support structure look like for CSM2 once CSM3 is released?
Good question.
That's a great question. Generally, we will still support a released version for like another 3 to 5 years, I think is the time frame. Development versions we kind of stopped supporting. But I think the key point is that because the CSM2 large ensemble is there, there's a version of that code that we will continue to support until there's a CSM3 large ensemble done. So yeah.
What do you mean by support there?
Well, it just means you know, we're updating it for new machines, you know, we're, you know, if there's a bug found, if there's, you know, that sort of thing.
So like if you want to run an experiment in the CSM2 large ensemble would be your control you're comparing against,
Right.
then you want to be able to run the same version and
Exactly.
still runs.
Yeah, so we'll continue doing that. And so, you know, because generally the porting experts, you know, they don't want to have to deal with bringing it to new machines as they come out and stuff like that for every single version. And so as soon as the CSM2 large ensemble was out, we stopped supporting CSM1, you know, and that sort of thing. That said, you know, you could still run it, it's still there. You know, it's just that it's harder for us to help you debug problems and things like that. So
I guess similar things for size 6 and size 5. So you're kind of supporting people doing experiments with both a little bit right now.
not so much. No, we've kind of moved on from size 5. I mean, there are still groups running it, and you know, you could talk to them, but in terms of the size consortium official policy, I think we're done with size 5.
So how many do you think? There's probably going to be some CMIP 7 groups that still run size 5, right?
Good question. I don't know. I don't know that there is actually, because as far as I'm aware, the main groups using SICE are the Australians with the Access NRI, us, and
Norwegians.
The Norwegians.
The Avian models not used?
No, a lot of the Europeans use the SI cubed.
Got it.
You know, the formerly known as LIM.
Got it.
So, yeah. So, yeah. So I don't think CMIP groups are going to be using size 5. Some of the operational centers are still using size 5. Some of them are still even using size 4. You know, but that's like for forecasting.
Yeah.
So.
Any other topics? Yeah.
I don't know if I think this is a longer discussion than we have time for here. I'm curious. I'm not sure what the right forum for this is, but like the sort of proliferation of the CICE model and the proliferation of options, and particularly if we start thinking about potential proliferation of emulators also within the model. I mean, I've certainly, I think, present the development challenge, both in terms of like, if someone new comes in to try to develop something in the model, it becomes much harder if they have to make it work with, say, 3 different pond schemes that are in the model, or make it work in a flow size distribution version and a non-flow size. Like, and I don't know if we have a sort of long-term vision of how to make that development like continue to be open to to folks who come in and, or, well, actually, there's a separate question about Los Alamos's long-term vision there, but like how to make it continue to be open, like, and easy for people to come up and get started while also pushing the edge of what's possible.
I don't know how this will all end up long term, but like as an example, within NCAR WRF, the atmosphere model, they used to have a ton of options and you can choose and mix and match. And in contrast, I think CSM has always had like, this is the group of configurations that we will scientifically support. And I think CESM will continue to do that. Like, okay, there might be 3 pond options, but we're using this pond option. This is something that we've scientifically validated. People can always take the model and turn on other ones or do development or whatever, but we're not necessarily going to support it scientifically, or, you know, if you're running into major issues, you know, support it software engineering wise. You know, I think that aspect may be the case. I don't know what'll happen with the emulators. You know, as you said, there'll probably be a big increase in those sorts of things. But CESM more traditionally has been like, okay, well, here's what we will support, and that's the release version of the model. and further development can happen from there, but it's not like we're supporting every pond option
Right.
from here to eternity.
It's a great question. I don't have a really good answer, but you look at CAM, for example, developed in-house, right? They had this whole SEMA project in which they're bringing in all these different dynamical cores into the CAM model. And so in theory, they're supporting a number of different atmospheric dicore options and, and their software engineering support to help with that. But I think Alice's point is important too, that, as a group with CSM, we're going to go with one configuration, and that's what we'll mostly.
So I think it's also a question for the SICE consortium.
Yeah.
Right? Because that's where this is.
Sure.
It's not
Sure.
with our
Sure.
version of the model, we can pick
Yeah.
some configuration. But if you want to get stuff back into the SICE consortium, it has to work with all
Right.
the other things that they are supporting.
Right.
I do think that long-term, we as a group should think a little bit about the SICE consortium and the longevity of the SICE consortium
Yeah.
and
Yeah.
viability of the SICE consortium. I mean, if Los Alamos is no longer investing in the SICE consortium, Elizabeth Hunke is managing this in her retirement.
Right.
Because she is just a lovely person
Right.
and feels really strongly about sea ice.
Right.
I mean, how long is that?
Yep.
Our CESM development cycle is about 8 years. In 8 years, will there be a SICE consortium?
Right.
Does that mean that we take the current version of SICE and then just as a group, we do our own thing with it and don't worry about
Right.
whether it works with the topo pond scheme or whatever, whatever thing we're going to just say is not our path forward? That's a much longer term perspective. Might be after my retirement, but anyway, I mean, I do think as a group, we should be thinking about that too, because I'm not sure with the SICE consortium,
There are
Yeah.
other challenges
how
there
long
too.
it'll
with,
last.
Right.
Like our international
Yeah.
collaborators.
You're taking over for Elizabeth, right?
Aaron's like,
Into the internal things, I think there's also challenges in the SICE consortium right now with our country's geopolitics, where we have
Right.
those collaborators who are being told we potentially can't collaborate with you
Right. Yeah.
because your country is
But
aggressive.
Canadians.
right. Those Canadians. Yeah.
Canada and Denmark specifically
Right.
been
Yeah.
part of the
They've been
consortium.
sort of told, yeah. I will say presently, forgetting for a second about maybe the consortium future. We do have a method which we can designate things for deprecation. And we've started to do that. So the original CSM pond scheme that Marika and I did is gone. Now. I know, right? Well, it was sort of superseded by the level funds because it did a sort of a similar thing, but
not forgotten.
yeah.
There's actually a version in the sea level ponds. If you set the options correct, the hidden options, you recreate.
You can get that back.
So
yes. But like there was this, Z salinity calculation in the ice and stuff like that. That was deprecated, and so there is a process where we've gone through and we said, is anybody really using this? And the thing is, it's like, if you are still using it, well, use SICE 4 or use SICE 5, use an older version of the model, and we just, but because for exactly that problem, we can't really support all these different things and all these different options all the time. So we're never going to get rid of the bits and lips thermo, but I'm just saying, but there are candidates for things in there that we could think about,
What about the old CESM albedo? CSM 3 albedo?
Yeah, that's a good question. I think we were thinking about getting rid of it, but I think that there was,
Don't get rid of it.
yeah, but I think there were still a lot of groups.
Well, because for exoplanet research, it's a pretty big
Yeah.
help to have that.
And it's-
ability
and
to
it's a lot-
prescribe the albedo rather than to go through the delta editing.
Right. It's a lot easier to tune than the Delta Eddington, and there's a lot of things there. Yes. That conversation has come up, but I don't think it's a candidate to deprecate at this point.
I
So,
mean, it's like 4 lines of code.
right. Yeah. It's pretty easy generally. So, yeah.
It's not, it's more than that.
Yeah, I mean, I think that's a really good point. There's a question about deprecation, but then there's also a question about sort of proliferation.
Yeah.
Have there ever been like, have there ever been any like software oriented conversations on that side about like, because from a very high level, I'm imagining there's a way to like structure your model such that you're modularizing it in a way that informs how you design a parameterization. And it's like, I need to get these specific outputs to plug into this specific part of the model, and I will design my parameterization around obtaining those specific outputs, such that you could like more easily just be like, I can sub one thing for another in this particular place, like an emulator or a morphically, or like, have those conversations happened at all for SICE specifically?
I'm trying to think of an example. Yeah, I guess I'm not entirely clear on where you're going with it. Because when I think of software infrastructure things, I think of more input, output, you know, history variables sort of stuff and that sort of thing. But in terms of just calling a different subroutine somewhere and stuff like that, I mean, we've definitely supported that, you know, normally with an APIS flag somewhere that says you want option 1, option 2, you know. So I don't know if that gets to what you're asking.
I think it does a little bit.
Okay.
I'm kind of trying to respond directly to David's question about like, the implication of like, how do we make it easier for people to develop for the model?
Right.
And I'm wondering if there are some solutions in there in terms of just like basic code design that would be possible to implement for an existing model.
In my opinion, I think it's already, at least IcePack is very modular.
Okay.
Right.
Like everything that it does. So when I made like all my parameterizations, I just added a new Fortran module, and then it just was the subroutine.
That kind of stuff is fairly straightforward. The other thing I have run into when I try to take old code and make it more modularized is that when you actually compile the code, often moving what is mathematically the same operation into a subroutine ends up with non-bit for bit repeatable stuff. And so there are some complications there. I guess maybe what I'm more thinking about is less the like nuts and bolts of getting the software right, and more like we have this expansion into a flow size distribution.
Yeah.
Andrew Roberts has an expansion into a macro porosity distribution. I argued yesterday that conceivably you should have the ponded ice should be represented, right? You should stratify your like the ITD basically. There's all these different places people might want to go from just an ITD to a joint something else distribution. And like large scale, I think it's helpful to do that. Because you could imagine the scenario where someone had said, like, we are never going to like logistically support adding another distribution on, then it's not necessarily worth the effort in doing that.
You mean like avoiding like the WaveWatch free problem of having like six ICE attenuation schemes that aren't supported are just kind of fallen by the wayside?
Yeah, like
tried to add something else and then one of them breaks and then
stuff like that. Or like imagine that Andrew's macro porosity scheme had become part of the standard model before the flow size distribution had. How much extra effort would it have been to now, instead of to add the flow size distribution onto a model that already has an established joint ITD macro porosity distribution? Like,
there's no official consortium decision about something like that. I mean, I think, if you want like a melt pond joint distribution, whatever, working with people in the consortium to figure out how to make it work. And if someone didn't want that, have it easy to turn off. All those things would be part of it. So it would be a significant amount of work on your part. I don't know that the consortium has a process for like, nope, we're not doing any more joint distribution. That's too hard. I don't think that's the case. It might be a little bit like the SSC thing where, okay, what's the scientific value in this? Why is this really necessary? And how can we support it? I think that would be.
But I guess the process is you demonstrate it in IcePack, right? And then you say, look, this is important. And then the hope is that's enough to motivate.
No, you'd probably want to also demonstrate it in like a 3D.
Right.
Dynamically.
Yeah,
Dynamic.
in a 3D sense too.
Yeah.
Yeah.
I do want to point out it's 12:30. I think this is when officially we're supposed to go to lunch. Maybe it was 12:45 regardless. Is there anything, I want to make sure we get to the cafeteria before it potentially, because it was going to be lower staff today anyway. Are there any other burning comments, questions, things that people want to talk about?
We can keep talking over lunch.
Yeah, we could do that too. I was going to go down there and eat
I
lunch.
Just being informal.
Yeah. Well, as I said, please feel free to get in touch. We are friendly humans. Thank you all for coming, both people online and in person. It's been good to talk to everyone. Hopefully everything is normal-ish.
Thanks for organizing, guys.
Yeah, thanks.
Yeah, it was a great meeting.
Very much for organizing.
Yeah, good job. Okay.